Desligar. So good morning, everyone. So let's start the third lecture on regularity structure by Professor Zambotti. Thanks.
Thanks. Okay, so on Tuesday, I felt that my lectures were getting too abstract, that it was a bit tiring for you and for myself, maybe. So fortunately, then Luca gave a very efficient and more down to the earth talk. So so I changed a little bit plan. Instead of following the lecture notes as I had planned, I'm going to, I call this chapter a digression, which is hopefully more, say, introductive. Of course, the introduction should come at the beginning. But now that you have already seen some, at least, of these notions, I think this is also a good moment to tell you what I'm going to tell you. So now let me go back to the classical, say, one-dimensional. So one-dimensional means the parameter time. So SDEs that you saw in detail last week. So SDEs are, in particular, so some SDEs are of this form. You have Brownian motion RD, you have a smooth coefficient sigma, and an initial point y0. Then the Ito integration theory gives well-posedness of this SDE. You need sigma to be Lipschitz. I'm not giving the details, just the general picture. And so the Ito theory is a very successful object with many wonderful results, etc. So you also have a notion of integration. So on one side you have a process which belongs, let's say, to the class of semi-martingales, or a martingale, or a local martingale, and you have a process H, predictable, locally bounded, etc. So let's say you have some class of pairs HX for which the Ito stochastic integral is well defined as a, I wrote local martingale. If X is a semi-martingale, it's rather a semi-martingale. Good. So this is something that probabilists are, say, familiar with, that they like a lot. Now, this marvelous theory is based on measurability. So you have random variables, So random variables are, by definition, measurable objects. In particular, measurability of the maps, so X to the stochastic integral, and B to Y, so where Y is the solution to the SD. But in general, the question of continuity of these maps is not even mentioned in courses on stochastic analysis, in books on stochastic analysis. So in fact, within the Ito theory, this continuity in general fails. So it's easy to build counterexamples. You cannot extend the map from B to Y to the space of continuous trajectories, for example, the space of Hölder trajectories. So this is known to be false in general. On the other hand, the continuity is usually a very useful property when you have it. So it's an interesting question to investigate when and how such continuity can be recovered. And in fact, so Terry Lyons introduced rough paths with the aim of filling this gap. And okay, this is the theory you saw last week with Sebastian Riedel. So here I am just reminding you, it is a slide from from Tuesday. So how do you replace the Ito integration? So there is this notion of rough integration. So you have an alpha which is between 1/3 and 1/2. You have a rough path. So later I redefine what a rough path is. But since I suppose you follow the reader's course, it's not necessary now. So you have a controlled path. And now, so what happens is that you build this function xi. Again, so Massimiliano would call this a germ. And this function xi is amenable to be so, I mean, you can apply the semi-lemma to this and obtain what is called the rough integral u y dx yu dx u, which is defined in this way, etc., etc. Okay, so what is happening here is that so instead of x and say h, okay, this was before h, now it's become y, sorry, you have a pair and a pair. So you are doubling the number of objects. So in a sense, this would be the ingredients of the classical, say, Ito integration theory. But now you have two new ingredients which are essential in this setting, okay? So I'm going to explain this better. So this is what I'm saying. So we are replacing just x with a couple of objects, so x plus something else, and y with a couple of objects, y and y prime. And the theory says that now this map is indeed continuous with respect to natural distances, okay? I'm not giving details, but the message is that you need to add some information, and then this will become continuous. So here I'm vague. I'm going to be a little bit more precise later. It's just to present the general topic. So, and this is related again to the fact that there is a product which is ill-defined. So you are considering. Okay, here I am in the setting where x, I said, is essentially C alpha. Okay, I'm supposing that y is also C alpha. Alpha is less or equal than 2. And now, so the derivative of x will be a distribution of order -1/2 or less. And then, if you remember the condition of the reconstruction theorem of these singular products, when the sum of the regularities is non-positive, then the product is not canonically defined, is not uniquely defined. And therefore, this object is not standard, it's not classical, it's not what you learn in classical calculus, okay? In classical deterministic calculus. So in stochastic calculus, you learn the Ito theory, but the Ito theory is based on martingale, so it's not the same point of view. Here you are really considering this pathwise in a sense. You fix omega and you consider this product as a product of a function y and a distribution x. Okay, so it's really, in the end, you want to be the same thing, but the point of view is really quite different. Okay, so another way to discuss this is this point that I did not want to discuss on Monday and on Tuesday, which is this multiplicity of a choice of an integral, of a product, and then the integral of the product. So again, I define this germ, which actually is the same which appeared here. Okay, so yeah, it's exactly the same, but with a different notation. Now, an integral of y in dx should have this property that, so if you go from s to t of uy dxu, sorry, yu dxu minus this quantity, okay, then you want to be able to write this, and then, okay, maybe a little bit formally, but you expect that this is of order t minus s to the alpha, and then the integral is also of the order t minus s to the alpha, and then you obtain order t minus s to the 2 alpha. Okay, so this is indeed a notion that makes sense. But now suppose that you have one such integral, so one function from 0 of time which satisfies this property. Is it unique? Now, if g is in C2 alpha, then y bar equal to y plus g will satisfy exactly the same property, okay? Because, sorry, this is a typo, this should be is. Okay, so this is of order t minus s to the 2 alpha. This is also of order t minus s to the alpha, so that the sum has the same property. And vice versa, if you have two pairs of such integrals, you take the difference, this cancels, and you get that the difference is of order also 2 alpha. Okay, so in this setting, which includes Brownian integration, the product we were mentioning here is really not uniquely determined. You do have a choice, because as soon as you have one, and there is a theorem which says that there is always one possibility, then you have infinitely many choices by this kind of modification. And then back to Ito. So one, for the first example you can think of is to consider the integral of Bs dBs. Okay, so if you choose the Ito version, then you know that this is 1/2 b squared t minus t. But you also have the Stratonovich form, which gives you rather 1/2 b squared t. Okay, now the difference between this and this is clearly gt equal to minus 1/2 t, which is of course C2 alpha. Okay, for any alpha less or equal than 1/2. And this shows already two important examples of the product Bs dBs that you can choose. Okay. So by the way, we are very fond of the Ito integral, again because it gives a martingale. So in a sense, we could say that it is more important than the Stratonovich integral. But at the same time, the Stratonovich integral is more natural because it looks really like so it satisfies a property which is like that of classical calculus. So the integral of Bs dBs, if B is C1, then it's exactly this. So here you are adding a quantity minus t, which is constant, but at the same time, it's clearly not a function of B. Okay, so it's constant. So it is a kind of probably artificial, say, additional term. Okay, which works and has many properties, but if you think of it, it's not so maybe so natural. But okay, it works. Okay, so now, how do you treat SDEs in this setting? Okay, so let me go more directly inside this discussion. So we can consider controlled ODEs. By the way, so this discussion is copied and pasted from these lecture notes I advertised with Caravenne and Gubinelli, which are on my webpage. So suppose you have a smooth X now, and you want to study this equation to start with. So it's a smooth version of the SDE if you want. Okay, now what do? So you are here. Yeah, you start, you see, here you add and subtract inside the integral sigma of ys, so in such a way that you can take out this, and you get this remainder, okay? Now, indeed, you call that R, and so you realize that when S and T are close, this is small, okay? Because, so this is, in particular, of lower order than T minus S, at least if sigma is good enough, so, okay? So the integral itself gives you already T minus S, and then the fact that sigma of YR is close to sigma of YS gives you an additional smallness, okay? So suppose that X is not so smooth, so that it is just a C alpha, okay? Then we would like to give an analog of this controlled equation. So we are saying that the delta of X, which is defined like that, has this behavior. Now, suppose that alpha is at least 1/2, then a solution to the controlled equation is, this is a definition, okay, is a Y in C alpha such that this quantity, okay, which is, this remainder, okay? It's the delta of Y minus sigma of Y times the delta of X is small, okay? It's smaller than T minus S with a quantitative information, okay? There is some exponent greater than 1 such that this holds, okay? So this is the Young stochastic differential equation. You saw this with Sebastian Riedel. Now, theorem, if alpha is more than 1/2, then for every X here and Y0, there exists a unique Y, okay, with this given initial condition and satisfying this. And moreover, the map from Y0 X to Y is continuous, so in the natural matrix, okay? By the way, I should have also written that this extends, of course, this notion extends the smooth one. Okay, so if X is C1, then you have the same. Okay. Now, the more interesting case for stochastic analysis is the one when alpha is less than 1/2. So let's say between 1/3 and 1/2. Then we have to modify the argument. So let us still suppose for the moment that the X is C1. So what we want to do is to go a bit further in our development. So we are here, okay? Then we, again, sum and subtract the sigma ys. And then the difference, we write it as an integral from S to R of something, which is equal to this, okay, by derivation of how do you say, the chain rule. And then this term, we do the same trick. So we take the value at S and then plus the difference between this is what, the V and the S, and this is still another integral. So in the end, so what we get is a term like that plus a remainder, and the remainder has at most this this behavior. Okay, so well, maybe the details are not so important. So the point is that by pushing the Taylor expansion in time to so a step further, we have obtained an expression like that. Okay, we have a first term which is the same as for the Young equation, but we also have a second term where there is a coefficient sigma 2, which is explicit, which appears. So nabla sigma times sigma. And there is a quantity which depends on x alone, which is our driving smooth path. And so this is the tensor notion, so tensor notation. Okay. And there is a remainder of order t minus s to the 3 now. Okay. Again, this is the smooth controlled ODE. Now, we introduced this notation, so I'm a bit changing from Reader's course. I apologize. So the first component of our rough path is this x1. The second component is x2. And these are the quantities which appear in the equation. Okay, so you see this is x1 and this is x2. And okay, one can notice that x2 satisfies this nice property, which involves also x1. So there is a relation between the two of them, and there is a estimate for both of them. And the ODE can be rewritten in a compact way like that. Okay, so this is always in the smooth setting. And now, again, let's suppose that x is of class C alpha, with alpha between 1/3 and 1/2. So x1 is well defined again, but x2 does not make sense anymore because here, sorry, where is it? Because here you are integrating with respect to x dot, and x dot is not defined if x is only C alpha. Okay, so there is a problem, and in fact, it is still possible to construct a robust theory for the controlled equation. So robust means that it includes this continuity property, provided we choose some x2 satisfying these two properties. Okay, so this is the algebraic expression you saw before. Sorry again. This, okay? It is a kind of weak formulation of this definition. Okay, this definition requires the existence of the derivative, but this weaker property makes sense also if x is not differentiable. So you need x2, which satisfies this and which has this control with two replaced by 2 alpha. So here 1 is replaced by alpha and 2 is replaced by 2 alpha. So the definition, so alpha rough path over the path x is a pair x1, x2 with so these properties. Okay, so x1 should be the increment of the path x, and x2 should satisfy this algebraic property plus the two analytical requirements. And then definition, what is a solution to the controlled ODE? So this is a function y such that now the remainder that I wrote in the previous slide is this. So you see it only depends on the solution and on the rough path, and then it should be less than t minus s to some exponent greater than 1. Okay. Now, theorem, let alpha between 1/3 and 1/2. So for every alpha rough path and the initial point, there exists a unique solution to the control ODE written in that way. And moreover, the map is continuous. So again, we recover continuity of this map. If you choose x to be a Brownian motion, then you can define an object where the second level uses, for example, the Ito integration. And then almost surely this pair gives you a rough path, and the corresponding solution, which is unique by the previous point, is almost surely equal to the unique solution to the ST. Okay, so this is extending the classical Ito integration to a more, say, general setting, because you can integrate, so you can replace B by other paths X in a continuous way. So this is the crucial property, but again, this is continuous if you consider also a second object, which means that the distance is strong, so the topology is strong, okay? And yeah, so this was the revolutionary idea by Terry Lyons at the end of the 90s. Yes, okay. Now, why is this relevant for us? Okay, so now I come back to SPDEs. So, because the regularity structures extend this approach to stochastic PDEs. Okay, so let us consider, for the moment, we have a smooth Xi on Rd. So this is just a function, a smooth function on Rd, R2 in particular. And this is the example that Luca already introduced. So I thought that it was a good idea to come back to this example and profit of this. So he already told you that we can write this in a mild formulation. So G is the green function of the heat kernel. So there is some function such that U can be written in this way: G convolution alpha plus beta U times Xi. Okay? Now, again, so this equation is ill-defined, which does not mean that it is ill-posed. It's worse. You don't know what the equation means. Okay? Sorry. Of course, not if Xi is smooth, but if Xi is in C minus 1 minus kappa, which is the regularity of space-time white noise, which is what you would like to obtain. Okay? So we are in the same setting as for the control ODE. We know what to do with a smooth object. We would like to extend this in a robust way to less smooth objects. You remember for the control ODE, I played with some expansions inside the equation. Okay? So now I want to try the same trick. Okay, you immediately see that the computation is a little bit scary, but okay, we can do it. So you remember U is equal to this. Now I'm just summing and subtracting U of X in the first line. Then U of X by the equation is the same object but computed at X. And then I do the same trick inside the equation. So U is U of X plus U minus U of X. So I do it here and I do it here. Okay? So, okay, another thing. Note that here, this would be U of Y. So there is another variable which is U of dot. Okay? So when you don't see the parentheses, it's because the variable is implicit. Okay, now what can I do? So here I have alpha plus beta U of X, which is a constant. So I can take it out of the convolution, and I get alpha plus b U of X times G convolution Xi minus G convolution Xi at X. So again, so here I have of Y, and here I have of X, but Y is implicit. And then I have what remains, which is beta G convolution U minus U of X Xi minus the same thing computed at X. So I have a function with an index X minus the same function computed at X. Okay, you see that even for a very simple equation, the notation are a bit heavy. But okay, we can try to make this a little bit more compact. So already Luca introduced this model. So for the So we have a list of objects which will be help us to have more compact notations. So in fact, we have one, we have x1, x2. This stands for the noise, xi. This stands for essentially G convolution xi. This is xi, G convolution xi. This is x1 xi, this is x2 xi. And one can compute homogeneities because this has homogeneity 0, this is 1, this is 1. The dot we said is -1 minus kappa, like space white noise. Yeah, I wrote space-time white noise, but there is no time here. So it's space white noise. This is G convolution xi is associated with 1. So it's this 1 plus 2. So it's 1 minus kappa. This is xi. G convolution xi is associated with this because you sum the two of them. So it's -2 kappa. And this is this plus 1, this plus 1. Okay. Okay, then this expression can be written in this more compact form. So ux multiplies the pi x of 1, which is 1. This coefficient multiplies the pi x of this small tree. And this is the remainder, where I remind you that the remainder is given by that. So by the way, you can already notice that, again, you have a Taylor expansion here, okay? Because this is a fixed function computed at y minus the same function computed at x. So again, Taylor expansions play a pervasive role in all this business. Okay. Okay. Are you okay with this? Now, in fact, it turns out that this expansion is not enough. So it's like for alpha less than 1/2, but greater than 1/3. So the first term was not enough to have a sufficiently small remainder. Okay, for the Serwi lemma, the remainder had to be of exponent less than 1. And we also need something like that here. Although in this case, it's also 1. So in general, it may be other exponents. But so in fact, we want to go further. And okay, we try with this. We try to have some terms of the form C1 times Y1 minus X1 plus C2 times y2 minus x2, and then the remainder is modified. It's r bar. It's this. Okay. Now we want r bar to be small around x. Now since r was already of this form, and we are subtracting this kind of term, in order to make this smaller than 1 minus k to the 1 plus kappa, for example, we don't have a choice. This has to be, again, a Taylor expansion at order at least 1, and then C1 has to be the derivative respect to x1 at x, and C2 the same respect to x2. And then we obtain that the new remainder has this form. Okay? And then our expansion takes this form, so it is ux times the pi of 1, plus this coefficient times the pi of this tree, plus these coefficients times the pi of the monomials, plus a remainder. Okay? Okay, until now, of course, everything is smooth, so you always have to think that what we do is in the aim of finding a limit, okay, a robust construction when your xi goes to a white noise. Yeah, and then here we go to this object that we discussed on Tuesday, which is the model distribution. Okay, so that's the point where we are going to a bit to take off. Okay, so please fasten your seatbelt and remain seated until the sign, okay, is etc. Yeah. So again, this is where the theory intervenes. Okay. Until now, we were just doing computations. Okay. But if you want to do only computations, you see, even for this small equation, terms can become a bit nasty. And that's why the theory really helps you. So I'm going to recall a bit of the definitions, okay? But I expect that this object, okay? So you see, I remove the remainder because like for SDs, rough differential equations, you don't know the remainder. It's something you do not control. So what you have is the model, which, as you saw, is an explicit object. So the model is given in this situation by 1, which is a constant. This is this explicit function of psi, which was written here. So psi is the noise. It's like X for the SDE. It's your control. It's something that you have in mind. So you have in your hands. And also G is explicit. And X, again, is just a monomial. It's also explicit. And the coefficients depend on U, which is the solution. But you are separating in this way, in a sense, the noise and the dependence on the solution. And you expect, okay, if you know the theory, you expect that this object has a good property. So it is a model distribution of exponent 1 plus 2 kappa. Okay. Before a little bit recalling you what this means, this should tell you in particular that well, this germ no, I mean, without the remainder, this germ should be coherent, and that its reconstruction should give you back the solution. So in particular, this has this, you have this way of computing the reconstruction, just computing for y equal to x. Okay, so I don't know, maybe this is a good point to go back. I don't see the pointer. Is there a pointer? No. Okay, it's a pity because I put, so I have manually to go back to page 41. No. Yes. Yeah. Yeah. So again, I show you the definition of a model, a pre-model, whatever. So this was the generalization of the rough path. Okay. And it is a family of germs with a matrix gamma with some properties. Okay. Apart from the technical definition, so this is what replaces the rough path. Namely, it is a function of your noise, which may be a bit complicated, okay? But at least you expect to control this almost surely explicitly, okay? Like the brain motion and its second iterated integral. And now the model distribution is something else. It is a function. By the way, pi is a family of distributions. So pi contains the dreaded distributions, but f is really just a function. So for every point in Rd, you have some coefficients which are indexed by your index set. And this is supposed to have nice properties with respect to the gamma of the model. Okay? And what is this built for? It is built with the aim of then building this this germ, okay, this linear combination of objects, which falls in the category of coherent germs. Okay, so there is here a parameter gamma, which is important. So the model distribution has, say, exponent regularity gamma. It's not really maybe correct to call it like that, but let's say in analogy with Hölder spaces, this is a regularity. It's really related to the length of your expansion. And here I have proved that indeed, when you do that, you have a coherent germ with the exponents alpha bar and gamma. And then plus you also have this uniform homogeneity bound with exponent alpha bar. So all this was introduced in the first lecture. And therefore, you can, what comes next? Well, no, not much. Okay, it was just to say that then you can apply the reconstruction theorem to this. So, yeah. Okay, so maybe if we go back now to our setting. So in the SD or in the rough situation, what we are saying here, what is it in the definition? Yeah, it is the following situation. This is the model, X is the model, and the pair sigma of Y, sigma 2 of Y is the model distribution. Okay, so you see for every element of your index set, so the index set here is 1, 2, you have a coefficient, and it's sigma of ys and the sigma 2 of ys. You see that also here, x1, x2 is, say, the noise part, and the solution to the equation appears only in the coefficients. Yeah, and now what we are doing here is the same, but in a more, say, a bit more complicated setting. The model, the rough path is, well, for the moment you have seen only 3 terms. Luca showed also the other ones. So this one, this one, this one, sorry, this one. So the remainder is always somewhat, how do you say? It's in a sense, it's your unknown. So you know it the least. And then you see that your solution has this, sorry, the solution goes inside the coefficients of your object. And now you expect, this has to be proved, it's not clear, but you expect that U has this property to be modeled with exponent y plus 2 kappa, which means in the end that indeed, so this germ is coherent and U is its reconstruction. Okay? Plus, what I don't really make explicit, all the continuities property which enter into the game, and which I will explain a little bit later or tomorrow. Okay, I know this is not easy, but can you see a bit at least that we are trying, what we are trying to do? So again, we are trying to give a rough, okay, description of this controlled PDE, and find a robust theory. So again, sorry, this like for the Brownian motion. So so here you don't see it yet because this is just okay. Let me think one. So this is still only linear in Xi. Okay, so you don't see yet the polynomial part in Xi, which is the non-trivial part. So you remember for the rough path, the second order is so it's quadratic in B. Okay, so that's the important. Now the quadratic part in Xi is going to appear soon. Now, for example, this is going to be okay, a bit more complicated, but let's try. So just a comment. You see that, so examples are not always the solution of okay, of a course. So the theory is hard, the examples are hard as well, okay? So at the same time, whoever told you that maths were easy? So let's try. So you see, we have constructed a germ which gives U as a reconstruction. Now, do we have a coherent germ? Of course, okay, U is equal to that, so, but which constructs this on the right-hand side, okay? It is non-obvious because on the right-hand side, we have in particular U times Xi, so we have to construct, to reconstruct the U times Xi, which means essentially finding, again, an expansion with respect to this Xi noise. Okay, let's see what I wrote yesterday. So now this is the rest of the model that Luca had already shown you. Okay, this is Xi. This is Xi times pi x of the tree, okay? And this is simple, it's just the noise times the variable xi. Now, we want to multiply Xi times alpha plus beta u, okay? So we know how to reconstruct alpha plus beta u because alpha and beta are constant, so it's just alpha plus beta u, capital U, okay? So this is easy, but then we multiply by the dot. So we do this a little bit formally using this product rule, okay? So when you multiply these two objects, then you put the dot. So this is just actually a graphical notation. So then you see, so the one times dot is dot. Dot times this is the other symbol, and then you have dot times xi. So you see, it's not so crazy, but this is formal. So you are just playing with symbols. Okay. Now the real work is to prove that that this is still a model distribution, and that it has still the correct regularity exponent, which in this case is kappa. So why kappa? Because I started from 1 plus 2 kappa. Since Xi has homogeneity -1 minus kappa, so I sum these two exponents and I obtain plus kappa, and kappa is positive. So actually 1 plus 2 kappa was chosen exactly in order to obtain this in the end. And then, I didn't write V is this. We obtain that R of this reconstructs this alpha plus beta u xi. Okay, then what we obtain the G convolution, this object. So this is equal to G convolution, the reconstruction of this germ. And then if you remember on Tuesday, at least this, I worked to show you that you can construct an operator on germs which commutes with the reconstruction. So G convolution R can be written as R, composition, this operator K. Okay, so K is this convolution operator on coherent germs that we discussed on Tuesday. Okay, but now, so with this, we expect to have another operator which is on model distributions and not just on germs, such that you can, again, commute with the operation of, yeah. So you want to put kappa inside, and this is called I don't know, bar, kappa bar, anything like that. So actually, this should have been the topic of today's lecture, but it will be just one slide at the end because I decided to concentrate rather on this digression. Okay. So now, in fact, this takes in our setting this form. So there is a general form for that, and it becomes here this. So you start from this model distribution, and you have an explicit form for this kappa bar, which, okay, fortunately, gives you the correct, the correct value in order to satisfy exactly what we want. Okay, so exactly to reobtain what we want, which is U. Okay, so okay. If you check, you have exactly the. You see, so this is U. This is the coefficient which multiplies the tree, and this is the coefficient which multiplies the monomial. Okay, now maybe the point of view that Luca was rather discussing was that of Picard iteration. So that's a bit the same. So you want to find U as a fixed point, okay, in such a way that this fixed point is a continuous functional of the noise in a distributional norm. Okay, so this is exactly the same as the rough path continuity property, but said like this, it is impossible. So you cannot control the behavior of V only, of the fixed point of this functional if psi varies in a distributional norm. But you can lift the equation to the space of model distributions. Okay, which is the same again in rough paths. You lift the SDE to the space of control paths. So you have this pair of coefficients. You don't have one coefficient anymore. Here you have three coefficients. You have the standard one plus the one which multiplies this 3 plus you have four coefficients. Sorry, plus these two ones which multiplies the monomials. And then you do a bit the same game. So you want to apply. You want to lift this map to the model distribution. So you have to multiply by xi, and you obtain that. You see, so the 1 is multiplied by the dot, the 3 by the dot, and the xi by the dot. And then again, you add the constants, and this is the form of the map. Now, again, maybe this takes time to digest, but believe me, so you have a map on model distributions which does exactly that. So you start from V, and then you obtain this, where small v is the reconstruction of capital V. Okay? Now, if you want to find a fixed point equation, right? So this is equivalent to what? So you have to equate the coefficient term by term. So this should be equal to, let's go back, to this, to U, okay? So U of X, so U should be equal to this, which is the controlled PD. So this is the starting point. So at least this is compatible. So then this should be equal to this, But this is just telling you that this coefficient has to be explicitly equal to that, and the same, so that the other coefficients have to be equal to that. So in fact, the other constraints here are not really constraints. They are once you have the solution U, fixed point of this, you know all the other coefficients, which is telling you that you're not really changing the equation. The equation is still the same. What you're changing is the topology, because you will have the norm of the big, say, U or V model distribution, which contains also some properties of these coefficients. Okay, so sorry, actually this should be the 1 plus 2k norm. Okay, all this is a construction in this space, makes this map a contraction for beta small enough. Okay, so once again, if you try to study this in a distribution setting, your estimates will not be good enough when Xi tries to become a distribution in C minus 1 minus kappa. But if you do this lift to this space, which contains these coefficients, and a norm which controls these coefficients in a good way, so then this turns out to do what it is supposed to do. So you obtain exactly that the map from the model to the fixed point is continuous. So this is exactly like the Terry Lyons theory. Okay, the fixed point is stable when the underlying model varies. Then you have almost surely, in the case when the model is constructed from white noise, which we'll discuss tomorrow, and also Luca will say something about that, then you have the solution to the, say, SPD that you were looking for. But you have extended this in a continuous way. So here we are not really saying what the topology of the model is. So this has to be made precise, but in a sense, you have to control each component PIX in the good C alpha I space. Okay, so at least if you want to give the idea, this is the idea. And also, if you want, U will be controlled in some C eta space for some eta. Okay? I have no idea what time it is. Okay. So what is complicated is, I think that first, as you see, the formulae are often a bit heavy, but so maybe if we go through the discussion again, so you are doing this like for the Sewi lemma and the control, the SDE or the control ODE. So you are writing local expansions of your solution. Okay, you are separating, in a sense, some functions of the noise and some coefficient which depends only on, say, explicitly on the solution. By the way, again, so this would be, even if he does not like the terminology, something like the Gubinelli derivative of u with respect to this part of the model, of the rough path, okay? And the next term, the same. So, no, where is it? The next to the next, this, okay? Again, what is it? So this would be the, okay, generalized derivative of u with respect to xi. So, of course, again, u is not C1, so you don't have a classical derivative. These are separate monomials, okay? So this is a classical monomial, this is a random monomial, and the expansion contains coefficients with respect to each of these monomials, and they give you this generalized derivative. Another comment, so this is u, and this is capital U. So what's the difference between capital U and U? Question, what's the difference? Like what is missing between the two pictures, you know, this, you have to find the difference. No one there? What? Pi is one thing, but that's not the only one. The remainder, that's more drastic in a sense. So here you are only collecting the coefficients and okay, the symbols to which they refer, but to go from capital U to small u, you need the remainder. Okay, so, and also this is something that at the start when I was studying Martin's theory, I didn't understand, so I thought he was making fun of me. So, because all these formal computations, okay, also in the next slide, you multiply by xi, so that's nonsense. So you are just changing the symbol. That's not a multiplication, okay? But the point is that you have this information which is very non-trivial and which tells you that you have behind the reconstruction theorem, which will give you the existence, sorry, of a remainder. So, okay. So again, what you need to go from capital U to small u is the remainder, and the reconstruction theorem is what gives you this this remainder. And it's the same for the Sewing lemma. The Sewing lemma gives you a remainder such that the difference with the germ is an integral. It's really the same philosophy. So therefore, again, as I was saying before, the fact that capital U is a model distribution and with a certain exponent is by no means a trivial information. So it's very strong information. And then the same discussion applies in the following. So once you start doing this kind of formal computations on the model distributions, this is, again, just a game. It's trivial. You're just shifting symbols on a list, okay, of coefficients. But that's the big part of the argument. So the fact that this is still a model distribution, that you have lost a bit in regularity, but it's still positive, and therefore you have a unique reconstruction, etc. Okay, so again, between exactly, between alpha plus beta u psi and this object, okay, the difference is that there is no remainder. So the remainder is reconstructed by the reconstruction theorem. And then here you have this operators, in fact, on model distributions. So the kappa, which is on general germs, and then the kappa bar, which is more precisely on model distributions. And again, this is a very strong information. So, so notice that, in fact, here I should have 2 plus kappa, okay? I didn't say it, but in fact, I project then on 1 plus 2 kappa because I don't care about the higher monomials, okay? So since I want to act on one space, which is 1 plus 2 kappa, what comes later is not interesting for us. So so the fact that this form is correct, again, is non-trivial. So you have to prove that this quantity is a model distribution with the correct exponent. Okay, and all this comes with controls on the norms. So the operators are continuous, how they depend on the model, blah blah blah. So we don't have time to do the details, but all this is done in the theory. Okay, and then again, when you go back to the equation, most of the work has been done, and at least in this case, in this relatively simple case, and yeah, so as I was telling you, the fixed point is giving you additional information on some functions of the solution, and this is what changes the topology in such a way that you will have the stability with respect to the noise. Yes. So, other comments? So, as already Luca is going to show you, in fact, what is missing still is the actual construction of the noise, sorry, of the model when Xi is spaced white noise in R2. So, as we have already said many times, in this business, products are what gives trouble, okay? In fact, you can do everything in this theory. The only, let's say, with the information that I have given you until now, you could essentially solve the problem. There is one point which is missing, which is this distribution. Because, again, you see that this is a product of distributions. We have said many times that, in general, this is not an easy thing to do. And now, if you check the regularities, so this is Xi is, we said, minus, maybe I write it, -1 minus kappa. The other one is 1 minus kappa. And so this is -2 kappa. So this is negative. And when psi wants to become a distribution in C minus 1 minus kappa, there is no canonical limit or a way to control this. Okay? And this really causes big troubles. So this is the next chapter, which is renormalization. And if you want, in rough paths, this is a bit nicer because at least you have, again, we have Ito integration, okay? So you see, that's not so different from this integral from 0 to t of Bs dBs. It's the quadratic object. So you see that this is the quadratic object, okay? So in fact, that's very similar, more. Yeah, so it's very similar to something like this, as if you were, okay, more precisely, this would be the analog of this, okay? So you have a fixed point S, which is X there, and you integrate okay, something which depends already on S, and then in dBu. Ito had already done this for us, so the rough path is relatively easy to construct. This is more complicated, and we'll discuss this tomorrow. But once you have the model, so once you have this product fixed, as for the rough path, you choose an object, okay? You choose it, say, I mean, also this, you choose it because it has good properties. For example, it gives martingales, etc. Or you want Stratonovich because you want the one, how do you say, so the classical calculus integration by parts, then you prefer Stratonovich. Here, you choose one as you, in the best way according to your problem, but then the theory works. The problem is that there is some explosion that already Luca is going to show you. Okay, so let me go to my last. So for today, I have another chapter, the shadow estimates for model distribution. So this should have been the content of the whole lecture, almost. In fact, it is reduced to one slide. So one slide with several typos. So given a model and a beta regularizing kernel, so with an additional technical assumption, which, okay, I do not discuss. So theorem, there exists, so this operator kappa bar, such that, wow, many typos. When you apply, so kappa bar to a model distribution in D gamma, pi gamma, you are mapped into D gamma plus beta, pi bar, gamma bar, where pi gamma bar is possibly another so what this is, I have no idea. Probably it was it was 5 a.m. this morning, so be patient with me. So you go to this space of model distributions by improving the regularity, or at least having a longer expansion, and then the property that you want is that so the reconstruction, the convolution between K and the reconstruction should be the reconstruction of, yeah, so I will write this on the blackboard. K, convolution, reconstruction of pi v should be equal to the reconstruction of what? So you are on the new model, so that's pi bar, and then you are applying k bar to v. Okay, so you remember, if this is a model distribution, then this is a coherent germ, then you can reconstruct it, and this should be the same as reconstructing at the start and then taking the convolution. So it's the good way of commuting with the convolution. And moreover, if you remember the convolution operator acting on coherent germs, then it's the same, but in fact here you're only but this should be pi bar. So so this should be pi bar k bar of v. The bar. Okay, this looks abstract, but then if you really go back to the computations we did before, it's really, it can be made more concrete. Okay, so again, I hope you appreciate that I did not spend 1 hour and a half on this, but I showed you something more concrete. And but again, I'm telling you, examples are great, but it's very easy to get lost in the computations, because you can have tens of terms. There is a very nice paper where the abstracts say, in order to prove this, it is enough to control a few hundred terms. Okay, so it's not to the paper is really great and does this very well, but it's just to tell you that if you want to remain always doing computation by hand, it's dangerous. Okay, so you need also the theory, which gives you at least a compact way to write these sums. And okay, so now fortunately we have Luca will explain things better than me, and then tomorrow we'll still have one lecture to discuss this, say the rest, okay, which is longer, but it will be concentrated, of course, in less than 1 hour and a half. Okay, thank you very much.
So thanks, Lorenzo, for the lecture. So are there any questions?
Is there in your theory any notion of persistence or anti-persistence along time, like, for example, characterized by the Hurst exponent, if you are familiar with that?
You mean Hurst in the sense of fractional Brownian motion, or what is it?
Things like this, yes. For example, the rate of the dollar changes every day. So if it was a normal Brownian motion, the movement up or down today would not know what happened yesterday. But if there is persistence, it tends to do the same thing as yesterday. If there is anti-persistence, it tends to do the opposite of what happened yesterday. Is there any notion like that here?
Okay, well, again, so you see that this theory tries to be as insensitive as possible to the details of the fine details of the noise. So this can certainly be applied to persistent noises, as you say, but then I guess these are fine properties which then have to be studied explicitly. You see, this does not give you a way to approach that.
Thank you.
Thanks for the talk. You mentioned on Tuesday that the proof for like the modeled distributions is quite different from the germs.
Yeah.
Are there like 10, 15 words that you can say what is the core difference, or it's just technical?
It's actually just technical. So you, okay, if you remember well, okay, first, what I can say is that, thanks for the question. So everything here is explicit. So the new model is an explicit function of the previous one. The value of k bar v is completely explicit. So it's really, okay, these are computations. So that means that you have to take the coefficients of the new model distribution and prove that they have the good properties. And you do that by writing each term as the sum of, it's in both cases, it's 5 terms, okay? What is puzzling is that the 5 terms are not the same. So I do not recognize one proof from the other. And actually, this one is easier. It's shorter than the other one, but I don't have yet really an explanation. So it's not very intuitive. So even the form of the operator k bar, it's not particularly difficult, but it's not intuitive. Yeah, maybe if you have the courage to read our proof, you may find some comment. So it's in the lecture notes, so it's available.
Are there any more questions?
In the example that you mentioned before, the solution is, I think, C1 minus kappa or something.
Yeah, probably, yes.
And in such case, the capital U, that is the model distribution, has a coefficient in front of the xi, right? What does this mean in this case? Because it cannot be the derivative, right?
Okay, sorry. First, well, in fact, the solution is smoother than that. So it's a function. Okay, it's not the solution itself. In the end, is a function. Okay, so then what is the question? Say it again.
It has a coefficient in front of the xi.
Yes.
What does this coefficient mean in this case?
Again, it's a sort of generalized derivative. It's not more. I cannot tell you more than that. You see, so the function is not C1, but okay, if you want, we can say, let's go back to the expression. So once you can see this like that, so you are expanding. So y of y minus, sorry, u of y. Okay, maybe even here. So u of y minus u of x minus this. Sorry, no, yeah, okay, it's here. U of y minus u of x minus this is equal to this plus this. So in fact, at that point, you can divide by y minus x, and you will find this coefficient in the limit. You see? So this, once you have removed this part, what is left has derivative, okay, equal to this coefficient. But the function at the start was not differentiable. You see, you have to remove this first component. But it's like for an SDE. Okay, let's take a semi-Martingale. So what you have? Xt equal to x0 plus integral from 0 to t bs ds plus integral from 0 to t hs dbs. Okay, so you know that x is not differentiable, but this is a coefficient, okay, with respect to ds, and this is so this is a derivative with respect to ds, and this is a derivative with respect to db, and it's the same.
Yes, thank you very much.
So one question is that in the example, no, that you mentioned, you have an elliptic equation, then the kernel is kind of very symmetric, right?
Yes.
And so does it mean that this when you do the computation, this pi bar is simpler than usual?
So pi bar, you mean at the end, this one, or?
Yeah, I mean because you have to add some elements, no, from pi to get pi bar, but
For example, psi is not symmetric, so
okay,
everything else is not symmetric. This is pathwise, so even if psi is white noise, you're treating it as a fixed object. So I don't see how the symmetry would help.
Another question. This is maybe a very naive question. So, when you said that Brownian motion is a rough path, right? Is it true that any martingale is a rough path?
Any martingale? Okay. Let's say. So, okay, more precisely, a martingale is just one step. Okay, you have to take the second step. So you mean the iterated integral? I should check. Maybe I'm sure that Peter Fritz would reply in a second. Probably that's correct. So again, if you have a semi martingale, you could have here a term which is not very nice. But if everything is 1/2 Hölder, etc., so I guess that's very reasonable. But I don't dare give you a answer if I'm not sure. So Martin, you know, yeah. Okay, I will write to Peter and
okay.
Exactly. There is certainly a paper by Peter.
Okay.
Thank you.
Are there any more questions, comments? So let's take again Professor Lorenzo. So before going to the coffee break, I have a short notice. Dick has found a card from the hotel here at Unicamp. So in case someone has lost the card, please let us know. In any case, we leave the card in the hotel.
So we're going to start the second exercise session on regularity structures with Luca Bru. And
okay, thank you. Okay, just as like time, today there will be no exercises, and I will continue the presentation and the discussion of the equation which I started presenting last time and which Lorenzo also discussed in this lecture this morning. Okay, let's go back to... Okay. So well, let's recapitulate what we have done last time. So we consider Gaussian white noise, coefficients alpha, beta real, and this fixed point equation, which, okay. In the last session, we have seen that in dimension 1, the Picard iteration can be done in a classical manner and everything works. But in dimension 2, it doesn't work anymore. And however, there was this heuristic which motivated the fact that this equation, instead of looking at it from the point of view of Hölder distributions, we should look at it from the point of view of germs, that is, families of local approximations. So yeah, instead of trying to find an actual distribution, we want to find a family of local approximations which correspond to this solution. And so we justified that the operations of convolution and of multiplication, at least when everything is smooth, we could lift them at the level of germs. And so we consider the equation under this form where K is the convolution operator for germs. And this product is understood in the pointwise sense, where when the noise is a modified version of the noise, and so it's smooth. And so with this formulation, if I can apply the reconstruction, then we obtain an actual solution of our initial equation. Okay, so which form should this germ f epsilon have if it is a solution of this fixed point? This is something that I started explaining last time, and which Lorenzo also re-explained this morning. So if you do the Picard iteration and if you reorganize the terms in a good manner, you will observe that the germs that appear in the iterations are of this form. So there are linear combination of basis germs pi I epsilon, which you can write explicitly. And which with each germs there is a symbol which represents what happens. So for instance, the blue dot corresponds to the noise. Putting a bar under a dot means convolving. And there was this symbolic product which corresponds to the product of two germs. Okay. Okay, so we if I remember correctly, we arrived at this slide. And now let's just for the interest of it, let's try to look at a few properties of the pi. So the first interesting property here is that if you consider two symbols, here the way we defined pi epsilon implies that there is some multiplicativity property, in the sense that pi epsilon of the product of two symbols equals the product of the two germs. Okay. And for example, if you recall the definition of pi x epsilon with these two noises on the bar, this is just this, and indeed you can just observe that this is the product of this, which is the pi epsilon of the lollipop here, and the product of the pi epsilon of the noise. Okay. And maybe just a remark is that this property here is maybe an artifact of the way we constructed the model, and is not an axiom for being a model. So in fact, the property may be lost at some point in the construction. And in particular, we do not expect this to remain true at the limit, even if the limit exists. And here it's even worse because the limit should not exist. And in particular, yeah, okay, why do not expect this to remain true at the limit if the limit exists is because this may become distributions. So the product of distributions in general makes no sense. And here in this particular case, if you look at this quantity and you take the expectation, you can see that it will diverge. So this motivates that even this, it cannot be satisfied when epsilon goes to 0. And the reason why this diverges is if you compute just the expectation of this, so we have an explicit formula for this. So when you take the expectation of xi is 0 because it's a centered Gaussian random variable. And so you obtain the expectation of the product of k-convol with xi epsilon times xi epsilon at y. And okay, this I think should be a y. So you can re-express this convolution as a xi tested against this modified version of the kernel times xi against the modifier or x epsilon. And by the isometric property of the white noise, this is just the scalar product of k epsilon and rho epsilon. And so this is this. And since the kernel k has a singularity at the origin, you don't expect this to converge. Because if you replace this by a function f, when epsilon goes to 0, this will just give f of 0. Okay. And so here, k epsilon 0 is plus infinity, so you expect this quantity to diverge. And in fact, in a later slide, we will see that it diverges logarithmically in epsilon. Okay. Okay. So now I'm done with what happens at the level of pi. And another very nice property to have is the property of re-expansion. And the fact here is that there exists a re-expansion operator, gamma. So this is the second part of the model after pi. And the gamma is defined by these relations, which means that the pi y can be expressed as a linear combination of pi at x. And the way to go from x to y is just through the operator gamma. So this is in the formulation of Lorenzo's terminology, and in the symbolic notation, it can be written this way. So pi y at epsilon of tau is pi x at epsilon of another linear combination of symbols which depend on x and y. Okay. So I've compiled a list of examples just to show you that this is really not complicated in general. So the first, maybe the first example corresponds to polynomials. So if you consider in general a monomial xk, what you want is to express pi x. You want to express pi y of xk as a function of pi x. Okay, and for this you just express pi y of xk. This is a okay. So you should imagine here that there is so this is a function or a distribution in general. So the variable of this function is the dot here. So this is just dot minus epsilon to the power k, and if you apply Newton's binomial formula, you can re-express this as a linear combination of dot minus x. Here it should be a L. Okay, and so exactly as the definition of pi x against polynomials, you see that this is pi x re-expressed against this linear combination of symbols, and so you just set gamma xy to be this this quantity. Okay. The second example would be the noise. So what you want is to re-express pi y of the noise as a linear combination of pi x of the symbols, but pi y of the noise is just the noise. It doesn't depend on y. So it's just also equal to pi x of the noise, and here gamma xy is just the identity. Pi gamma xy of the noise is just the noise. Okay. So pi y epsilon of the noise, by your definition of pi, this is the noise, xi epsilon. Okay, but you see that this doesn't depend on y anymore. So this is also a fortiori equals to pi x. Okay, and so since what we want is to express pi y in function of pi x, it means that I can just put gamma x epsilon to be of the noise to be the noise itself, to be the dot itself. Okay. Okay. So maybe to illustrate the effect of convolution on the re-expansion operator, again, you want pi y epsilon of the lollipop to be pi x epsilon of a linear combination of the elements in our structure. And if you write pi y epsilon of the lollipop, explicitly what we had in our table was this. So it's k convolved with psi epsilon minus k convolved with psi epsilon at point y. And to re-express this as a pi epsilon at point x, what we can do is just remove and add the quantity at point x. And so this is just pi x epsilon of the lollipop, and this is just a constant in x and y. There's no dot here anymore. Okay. So this line just equals pi x epsilon of the lollipop plus this quantity times the monomial one. Okay. And so you just set the re-expansion of the lollipop between x and y to be this quantity, which is what appears here. Okay. And maybe a last example corresponding to what happens at the level of the product. So if you consider this symbol, which is just the product of the lollipop and the blue dot, once again, you want pi y epsilon of this symbol to be pi x epsilon of a linear combination of the symbols. And you know explicitly what pi y epsilon of this is. Maybe I should have put a dot here as previously. And once again, the strategy is to replace this by the same quantity but evaluated at x. And so we add it to make 0. And once again, here what we obtain is the pi x epsilon of this symbol. And here what we gain is a constant time the noise. Okay. Okay, it doesn't depend on the variable here of this function anymore. So we can just rewrite this as a pi x epsilon of the symbol plus this quantity times the dot. Okay. And so once again, we set this re-expansion operator against this symbol to be this. Okay. And so, okay, I tried to justify that. So if you recall these two examples I did were the noise, the convolution, and the product. And so you can expect this kind of calculations to be done in a recursive manner. So in general, the gamma is calculated in this way. And here, so we can, I don't know if you see, but I tried to order the calculations into a matrix so that it's a bit visual. And so we see that the operator gamma x epsilon is just as Lorenzo described on Tuesday. So you see that it is a matrix with which is triangular, which has only ones on the diagonal. And okay, so this is what I wrote here. There is a property of Hölder continuity. So if you consider every entry of this matrix as a property of homogeneity in x and y. So here we are in the situation where every entry in this matrix is what do you say? Is an increment of a function, but in general it can be just a two-parameter function x and y, and this two-parameter function satisfies the property of homogeneity. So here you see that this is more than x1 minus 1 minus y1, and this by the classical Schauder estimate, this is smaller than x minus y to the power 1 minus kappa. Okay. Okay, so these are the two properties which Lorenzo would say imply that the pair is a model. And there's a further property which is quite interesting, which is the group property, which means that basically when you re-expand from x to y and then you re-expand from y to z, it's like you're expanding from x to z. Okay, so you can check this by hand or by multiplying this matrix, or whatever you want. Okay, so this has some nice properties, and yeah, I think it's nice to have this visualization of what the re-expansion operator is in this case. Okay. And the consequence of these properties is that if we put pi epsilon and gamma epsilon into a pair, it defines a model. Okay, so if I understand correctly, there are different terminologies for what a model really is, but in pretty much all the terminologies, this is really a model. Okay. Any questions so far? No? Okay. So just as pi had nice properties, let's look at the properties of gamma. So the gamma also has a property of multiplicativity. And you can observe that the gamma of the symbolic product of two symbols is just the product of the re-expansions. For example, if you look at gamma of this symbol, which is so the symbol is the product of the dot and the lollipop. And we calculated this re-expansion operator against the symbol to be this. But this is just the symbolic product of the lollipop plus this times the monomial 1 against the noise. Okay, and this we calculated it to be the re-expansion of the lollipop, and this we calculated it to be the re-expansion of the noise. So in general, there is a multiplicativity of gamma, and in fact, this property of multiplicativity will generally always be true and will be guaranteed by. If you consider a general equation, this property will be guaranteed by the algebraic construction of the model that we can make. Okay. While the same property for the pi was just a coincidence of the way we constructed the pi. Okay. Another property which we can call admissibility property states that the following thing: the model M epsilon first acts the way we want under convolution. So this means that pi and gamma are transformed the correct way under the Schauder estimates. So in this sense, it means that pi and gamma is equal to the pi bar and the gamma bar that Lorenzo presented in his multi-level Schauder estimates. And this property is just the property of multiplicativity of the re-expansion operator. And why do I mean, okay, for this name, there is also, I think, not only one terminology, but several ones. So during these sessions, I will say that any model which satisfies this property for this in this situation will be admissible. And I will not adm the corresponding set of models. And the interesting consequence of this constraint is that if you consider any model which is admissible, then the re-expansion operator is automatically determined by the basis germs pi. And why is this? Well, because under convolution, you see that the gamma is determined by pi, and under multiplication, the gamma is just determined by the gamma itself. And since the construction is recursively made out of the products and of the multiplications and of the convolution, then you observe that in general, indeed, the re-expansion operator gamma, if you have this formula, then it will be automatically determined by the model, the basis germs pi. And so it allows to simplify some calculations later, because it means that when we consider a model, we can just consider pi, and we don't have to deal with what happens with the gamma, because it's automatically tackled by these properties. Okay. Another property here that is satisfied, which is more probabilistic in nature, is the stationarity. So if you consider a test function phi, an element h and a symbol tau, you can see that these processes, so they are random processes, because here the model depends on xi, which is random. And so the property is that this is stationary, in the sense that their law does not depend on the point x. And maybe to illustrate this in an example, if you recall the definition of the pi against the lollipop, you will see that this is just k convolve with xi epsilon at tested against phi x minus k convolve with k epsilon at point x. And so because of the properties of convolutions and distributions, you can just express this as a xi tested against this test function centered at x. Okay. And so the point is that the law of Xi only depends. So Xi is a normal one variable which is centered, and its variance is just the L2 norm of this. Okay, and the L2 norm of the test function here does not depend on the basis point where we center this function. So you see that this doesn't, in law, this doesn't depend on X. Okay. And one useful consequence of this property is that if I want to calculate this expectation of pi x epsilon of tau against this function recentered at x and rescaled at scale epsilon, this is the same but at the point 0. So in some sense, it allows to, in the calculations that will appear later, it allows to put everything at 0 and not care about all the reals x. Okay. Okay. So I think I just presented a few interesting properties of the model M epsilon, which we encounter in this situation. Now, of course, the model is just one part of the theory, and as Lorenzo explained, the model is the equivalent of Roth path, and the model distribution is the equivalent of control path. So if you want to construct a solution, we need to consider the model distributions. So recall that we are interested in germs that are linear combinations of these basis germs. And so basically what we're interested in are these model distributions, which are the linear combinations of the symbols, which satisfy these two properties, two estimates. And the advantage is that once you have a model distribution, if you let me say, if you take pi x of this model distribution, it makes a germ which is coherent, so you can apply the reconstruction theorem. So any model distribution is associated to an actual distribution via the reconstruction theorem. Okay. And so now it's a bit of what Lorenzo presented this morning. When we look at the fixed point of the equation, what we realize is that we want to set up the fixed point for the equation, but in the space of model distributions, which only correspond to these four symbols: the monomial 1, the lollipop, and then the two monomials x1 and x2. Okay, and explicitly, if you want to look at which germs or which families of local approximation it corresponds to, you can explicitly write it in this way. Okay. And of course, there are always these questions when you want to set up a fixed point. Here, the equation, you want to make products and you want to make convolution. So, of course, the question are, can you actually perform the multiplication? Can you actually perform the convolution at the level of the spaces of model distribution? So this is also what Lorenzo discussed this morning. Maybe the first result is that I can mention is the result of multiplication. So if you consider any model distribution of this form, which we assume to be in a model distribution for some exponent gamma, which we assume to be strictly greater than 1, because we truncate at 1. And now if we perform the symbolic multiplication of this model distribution with the noise, which we perform by, it's really in some sense symbolic, then you can prove that, I mean, if you look at the estimates of being a model distributions for this expression, you will see that they're exactly the same as the constraint of being a model distribution for this. Okay, so this new model distribution will actually be an actual model distribution where we have to subtract 1 minus kappa to the exponent, which corresponds to the regularity of the noise. And because the constraints on A, B, C, D are exactly the same for being a model distribution here or being a model distribution here, in fact, in this situation, we have a continuity bound, which is in fact the equality between the norm of f times dot and the norm of f. Okay. And so in general, here we've been lucky because we only had to multiply model distribution against a symbol of the structure. In general, there is also a multiplication result where we can multiply two model distributions against each other. Okay. And the second result of stability is the multi-level shoulder estimates, which Lorenzo also discussed this morning. It says that if you consider K to be the fundamental solution of the Laplacian, which is two regularizing because the Laplacian, is two derivatives, so it subtracts 2 degrees of regularity. The theorem says that there is an operator K between the model distributions of exponent gamma and the model distributions of exponent gamma plus 2, which commute with the reconstruction. And furthermore, this we can make this operator K explicit in functions of the model because there's always an underlying model when you consider model distributions, and it's explicit also in function of the reconstruction operator for this model. Okay, and there are also continuity bounds, like always. Yes. Oh, this means that I have to enlarge the compact. Okay, so this is the compact enlarged with enlargement alpha. Yeah. Okay. Yeah, because when you do the calculations, you realize that if you want to know information on the compact K here, you have to impose information on the compact, a slightly enlarged version of the compact K. Okay. Yeah. So B0R is just the ball center 0 and radius R, and this is just the sum as sets. Okay, and there is also maybe a third operation which is a bit hidden in the calculation. It corresponds to the truncation. So when you have model distributions, you have these expansions, and sometimes you want to truncate these expansions. And so the result of truncations tells you that you can do it in such a way that the truncation that you perform still gives you a model distribution. So if you consider a model distribution with exponent gamma, and you consider another exponent strictly smaller than gamma, then if you truncate f at level gamma prime, that means we remove all the symbols in the expansion that have homogeneity greater than gamma prime, then you also obtain a model distribution which is in the gamma prime. And you also have these continuity bounds. Okay. Everything good so far? Yes, perfect. Okay. So now when you combine these three stability results and you consider this fixed point operator, which at f associate k of alpha dot plus beta f dot. So this is just the lifted equation at the level of model distributions. Then this operator, you can prove that it's well defined. And you have the continuity bounds for P of f minus P of g. And so it's really similar to the calculations which I presented in the Holder case last time. So this is bounded by a constant time f minus j. And the small subtlety here is that the constant depends on the compact k. And here the model that we have depends on the noise. So in some sense, the Lipschitz constant will also depend on the norm of the noise and the compact k. So you remember, either you decide to work on the torus rather than ND, or you can decide to work with the weighted Holder spaces, but this adds technicality. So here you could, I imagine, introduce weighted versions of all the spaces which have been introduced so far. But this, this in some sense is a technical difficulty which I don't want to address. And so we can admit that just by setting beta small enough, this operator will become a contraction. And so as I already mentioned, if you reconstruct the solution of this fixed point, you obtain a solution to the original equation, where here we have still epsilon strictly positive, so everything is smooth. And at some point, we will need to address what happens when we want to make epsilon goes to 0. Okay, so okay, there are, in general, better continuity estimates than the one I've presented, in the sense that the one I've presented compared model distributions with respect to only one model. But in general, you can compare model distributions with respect to different models. And there are still very nice continuity estimates, and you can still perform the fixed point in this manner, which tells you that it furthermore gives you a result of continuity of the solution map. So it tells you that the solution map is the solution map of the previous fixed point equation at the level of model distributions. It will be a continuous, okay, for again, you know, metrics which I will not define, from some open sets of the set of admissible models into the set of model distributions. Okay. And so since the reconstruction operator from the set of model distributions to the set of actual distributions is continuous, what happens is now the map from the admissible models to the actual distributions is now continuous. So the question that we need to address to, in order to understand the convergence when epsilon goes to 0 is now the following. We want to understand how the sequence of model converges when epsilon goes to 0. Okay, because if the sequence of model converges when epsilon goes to 0, then you know, the map that maps a model to the actual solution of the equation is continuous. So we can make just epsilon goes to 0. Yes.
Thank you.
Yes, you can define a metric in this space. Yes.
Because I suppose this one is the analog of the, so in Sebastian Riedel's talk, there was this whole business about Banner space valued fields. And I suppose here it should be a Fréchet space valued field.
Yeah, so he had this discussion about the tube topology, if this is what you, but he said that in the case of Rothbard, this topology actually is metrizable.
Exactly.
Yes.
Is it here metrizable too?
Yeah, it's also metrizable.
Okay.
Yeah. So this is a really a complete metric space. Yeah. If I understood things correctly, yeah. Okay. So yes, you can undo these sets and spaces with topologies and even metrics if you want. But okay, it would be a bit ugly expressions to work with. So okay. So now we want to consider the question of whether the random sequences M epsilon converges when epsilon goes to 0 in the space of admissible models. And for these kind of questions, there is again a kind of Kolmogorov criterion, Kolmogorov's continuity theorem, which gives you a sufficient condition for the model to converge. So okay, well, I think I rephrased this result a little bit because it is not exactly written in this way in the original paper. But what the theorem says is that if you consider a sequence of stationary admissible models defined on some, say, complete probability space omega fp, then if you satisfy these two estimates, where, you know, like in the Kolmogorov's continuity theorem for distributions, which I presented last time, what you do is you test the model against a test function or scale at a scale lambda. You take the expectation, you take the pth moment of this, and you want to study the growth when lambda goes to 0. And then the second one is, in some sense, a result of the second one is kind of a Cauchy criterion. So you look like you look at what happens at two different epsilons, and you want this to be very small when the epsilons goes to 0. Okay, and if you have these two conditions, then the sequences of models, it converges in this LP space, model valued LP space. Okay. Okay, and the proof is as in the Kolmogorov's continuity theorem for distributions, which I presented on Tuesday. You compared what happens at dyadic scales using a wavelet theory. Okay, so you can use wavelet decomposition to show that this implies the existence of a limit, and the limit satisfies the properties of being a stationary admissible model. Okay. So, in some sense, if we want to consider the convergence of the family of models pi epsilon, which we have constructed, we need to consider this quantity and try to bound them. Okay. Okay, maybe just a remark is that so a priori a model depends also on the gamma, but the reason is that since here we consider admissible models, the gamma depends on the pi, so we don't have to assume further assumptions on the gamma to obtain convergence, because the gamma is determined by the pi. Okay. All right. So if you have no remarks or questions at this point, I will try to actually do some of the calculations. Oh yeah, maybe another remark that I have not made is that you need this property to be satisfied for symbols of negative homogeneity. The symbols of positive homogeneity, you don't really have to care about them. So, okay. And yeah, so exactly as in the case of white noise and Brownian motion, because here the objects that we have are Gaussian and the centered, their pth moment is bounded by their variance. So in our cases, it suffices to obtain the bounds for p equal to, and it will automatically give them for all p. Okay. So if you remember the list of symbols, the symbols which have negative homogeneity in our situations are the noise times the monomials, x1 and x2, and also this product of the lollipop with the noise, which I don't know how to call this kind of symbol. So we are going to show, at least in some cases, how to obtain such bounds. And maybe one remark is that already was hinted at by Lorenzo, is that the first three symbols are a bit simpler to analyze. The reason is that they contain only one copy of the noise. So there's no product, there's no product yet to consider. So they're in some sense a bit simpler to analyze. And this one, since it's the product, is the one that diverges, which I showed you in the previous slides. This symbol is a bit tedious to analyze. Okay. All right. So no, the slides contain a bit of calculations. So let us consider for instance, just the noise, the dot. So what we want to bound is this quantity, which is the expectation of pi 0 epsilon of the dot tested against a test function rho scale at scale lambda. And we take this, we want the variance of this, basically. And in fact, by definition, pi 0 epsilon of c dot tested against phi lambda, this is an explicit quantity. Explicitly, this is a xi epsilon, because this is just xi epsilon. This is xi epsilon tested against phi lambda. And xi is just xi convolved with rho epsilon. And by the properties of distributions and convolution, distributions convolved with a test function is just a distribution tested against this test function. Okay, so xi convolved with rho epsilon tested against phi lambda is just xi tested against rho epsilon convolved with phi lambda. And now by the property of isometry of the noise, this expectation here is just the L2 norm square of this quantity. So you see that now the noise has completely disappeared, and we just need to make sufficiently good estimates for this norm. Okay. So yeah, this is now depends only on the modifier rho, the scale epsilon lambda, and the test function phi. And okay, there is a simple inequality in general which allows you to evaluate LP norms of convolutions, which is the so-called Young's convolution inequality. which tells you that the convolution f convolved G in norm LR is bounded by the product of the norm LP and the norm LQ as soon as you have this constraint of conjugation and the exponents. And so, for instance, if I take here R equals 2, P equals 1, and Q equals 2, you see that this satisfies this this conjugation property. And the consequence is that the expectation of this, now we can bound by the L1 norm of rho epsilon square times the L2 norm of phi lambda square. And so because of the scaling that we chose, the scaling that we chose is the L1 scaling, basically. So it is invariant by L1 norm. So the L1 norm of rho epsilon is just the L1 norm of rho. And on the other hand, when we consider the L2 norm of phi lambda, there is a multiple of lambda that goes away. So here we have lambda to the power minus 2. And so if you look at what was the bound that we required, you see that this gives the correct bound as lambda goes to 0. Okay. Maybe when you consider the second bound, it's a bit more complicated. So exactly in the same way, you can calculate explicitly what this quantity is. So here it's rho epsilon 1 minus rho epsilon 2 convolved with phi epsilon L2 squared. And so once again, this does not depend on the noise anymore. And you just have to just, matter of doing calculations of L2 norms and the convolutions and everything. So, okay, the way I bounded this norm was to consider this function, which is just the difference of rho epsilon 1 or rho epsilon 2. And you observe that because rho is of integral 1, and the integral is invariant by the L1 scaling, then this integral is 0. The integral of this test function is 0. So when you, when you perform the convolution here, you can just say that this is the integral. You can subtract this term, in fact, in the expression of the integral, because this term evaluates to 0. It depends only on x and not on z. Okay, and so the consequence is that you can explicitly write this L2 norm squared as a triple integral. So the integral of rho epsilon 1 epsilon 2 of z1, rho epsilon 1 epsilon 2 of z2 times a function which is itself an integral. And since this is increments, you can use Hölder bounds to bound them. So you can do a natural change of variable, use the fact that the test function phi is Hölder, and then you obtain the bound that you want. Okay. So maybe I shouldn't enter too much into the details because it's just calculations which are not really related to what we're doing in general in regulatory structures. Okay, the second example that I considered was the product of the noise and the monomial. And you can see that in some sense you can express this. Okay, so what happens is that the estimates, you can perform exactly the same calculations as for just the noise, and the estimates that you want, they just follow in the same way. Maybe I will not enter into the detail. And so the more interesting term here is just this symbol which contains two noise. So it's a product of two noise. So this is a bit more complicated. And in fact, when you express this explicitly, this is we know what it is because everything is explicit in our calculations. So this is just this integral. Okay. And once again, k convolved with psi epsilon, k convolved with k epsilon, we can express this as psi evaluated at k epsilon, okay, modification of k, modification of k. And here you see that in this integral, there's a product of psi and psi. So this is a bit more difficult to estimate, because we cannot just directly square this. So if we take the expectation of this square, we have 4 noises that appear. So this becomes a bit more complicated. to estimate a product of 4 noises. And so a useful tool is what is called the chaos decomposition. So I will not enter very much into the detail. I will just present in one slide what is the tool that we will use. Here, because Xi is a Gaussian white noise, you can prove that there exists an explicit map between this space, which is the sum of the tensor products of L2 of RD against itself. You can map it into L2 of omega FP in such a way that when in this sum you only have one term. In the tensor product of order 1, I1 of F is just the noise tested against F. In the tensor product of order 2, I of the tensor product is I1 of F times I1 of G minus Fg. So this is just Xi of F, Xi of G minus the L2 scalar product of F against J. And in fact, if you wanted to consider more complicated situations, there is a general product formula which allows you to express IN of tensor products as a linear combination of the smaller indices. And so why is it interesting is that here we have Xi tested against F times Xi against J. We have an expression as I2 on the scalar product. And why is it interesting is that because there is this isometry property, pretty much, or quasi-isometry property here, which tells you that IN of F square is bounded by just the L2 norm of F. Okay. Maybe this is a quite general result. And okay, so this is a lot of calculations, but if you consider what happens here, you have the noise tested against a test function, the noise tested against a test function, and so you can just say that this is I1 with the formulation of the previous slides of this test function, I1 of this test function. And what we have seen is that I1 can be, this product of two noises can be decomposed as I2 of the tensor product of this plus the scalar product of this and this. Okay, and because the map in the previous slide was linear, this is I2 of this big integral plus just an explicit. I mean, this is just deterministic now. Okay. And so we get a decomposition, which we can call chaos decomposition, because, okay, here are the term of homogeneous chaos 0, here is the term of homogeneous chaos 2, and in general, you can continue the expansion in a more and more, in a systematic manner, if you want. And so it suffices to estimate the three terms that appear here separately. So remember that the k epsilons converge with rho epsilon is the term that we already encountered before. I said it diverges to infinity. And in fact here, because k is, I mean, the fundamental solution of the Laplacian is just explicit. It's the logarithm times -1 over 2 pi. So C epsilon, you can just perform the scalar product. And because the log appears, you know, you have a log of epsilon z, and because the log, yes, 5 minutes, okay. Because the logarithm transforms the sum and the products into sums, this is just a log of epsilon plus a constant. Okay, so this diverges logarithmically. All right. For the second term, one property that we can use is the singularity at origin of the kernel k. Because you know that k of x is bounded by, so this k of x is the logarithm, so it's bounded by any negative power. And this is a property that is preserved by modification. And so you directly obtain that if you do the usual change of variable, this integral is just bounded by lambda to the power -2k, and this is the bound that you want to have. Okay. And for the third term, you can use the isometry property, which tells you that the expectation of this squared is just bounded by the L2 norm of this integral, where here the L2 norm is in L2 norm in in two variables, because here there are two variables here and here. Okay. And here, so you see that this bound is again just explicit in functions of the kernel K, the modifier rho, and the scales epsilon and lambda that you want to consider. So using again the singularity at origin of the kernel K, you can prove that you should do the calculations, which I don't want to do here. Yeah, you can prove that this is bounded by lambda to the power minus 2 kappa. And this is what we want. So the conclusion of this calculation is that the two terms that are here, they have the scaling property that we want when lambda goes to 0. And unfortunately, this one, it diverges. So that what we obtain is that, okay, here should be a 0. So the model here is, okay, because this is just pi of the monomial 1 tested against phi x lambda. So this shows that the model pi at this symbol is just pi of c epsilon times 1 plus terms that we can control. Okay. So this shows is that what this shows is that the sequence of model m epsilon, it diverges. But if we consider the renormalized model defined by this, so nothing changes except for this symbol which we subtract, for which we subtract a constant time 1. Then this new renormalized model converges as epsilon goes to 0, and you see that the constant here diverges logarithmically. And so by continuity of the solution map, now the reconstructed solution corresponding to this model also converges in the sense of Hölder distributions. Okay. Okay, I wrote explicitly the renormalized model, so you see that it's exactly the same, except for this symbol for which we have to subtract this constant epsilon. So a few remarks that naturally come with this is that, okay, here the re-expansion operator for the renormalized model is the same as for the original model. And in particular, so you observe that pi is not uniquely determined by the gamma, even for admissible models, even though the opposite was true. In general, the fact that the two re-expansion operators coincide is not true. Here is just a coincidence. And you observe that the basis germs pi, they used to be multiplicative when I first constructed them, but now they are not multiplicative anymore because of the constant that was subtracted. Okay. And okay, I don't think I have much time left, but what you can do is that you can, because now you have a new distribution at the limit. And of course, you need to know if it actually corresponds to an equation, because in some sense you have changed the situation. And you can prove that the new, with a few calculations, you can prove that the new renormalized solution satisfies this equation. So the constant C epsilon appears now in the equation. Okay, and the final remark is that as Martin Herrer has mentioned in his Young Myth lecture, you can replace the constant C epsilon by C epsilon plus C for any constant C in R, and you will still obtain convergence. So in this sense, there is a whole family of solutions indexed by R in this case. Okay. Okay, so I'm done. Thank you very much for your attention. And do
you have any questions for Luca?
Is the calculations for the two dots and
yeah.
that term, is it written anywhere? Do you have the complete calculations for that?
Yes, in fact, it was already in the original paper by Martin Herrer, but in a different context, in the context of
PAM.
PAM maybe.
Yeah. I mean, I was wishing for something else because I couldn't understand the argument there. So.
Yes.
But you don't have any.
No. This is just a rewriting of what was already done in 2014.
Oh, thank you.
Any more questions? So let's thank Luca again.
Okay, so good afternoon. We continue with Martin Harris' course on Young Mills, the third lecture. So please, Martin.
Okay. Yeah, so today what I want to do is discuss a bit the choice of state space for this Young-Mills evolution. So remember, what we did last time is we said, okay, you want to somehow give a meaning to the measure, which would be something like e to the minus Young-Mills action times Lebesgue measure on the space of connections. And then what we said is, well, if you want to give a meaning to that, you can try to give it a meaning as the invariant measure for the sort of stochastic gradient descent flow that corresponds to it, which would be some sort of a derivative of S of A plus a white noise. And then what we argued is that, well, if you write down this equation, if you sort of take the functional derivative of the Young-Mills action, you find that because of the presence of gauge symmetry, so because you have this big infinite dimensional symmetry group, there's lots of degeneracy. And the consequence of that degeneracy is that this guy is not elliptic, so the equation is not parabolic. But then we argued that you can actually add to this equation basically any term which sort of pushes you only in the direction of gauge orbits, and that by doing that, at least formally, you wouldn't change the invariant measure, right? You would change the dynamic, but there are lots of dynamics that have the same measure as invariant measure. And so the argument here was that you could add anything of the form dA of anything you want, and as long as it's of this form, it shouldn't change the invariant measure. And then we saw that a natural choice here is dA d star A. Actually, I had one remark. Someone asked me, why didn't I put an A here? And well, you can. It's actually the same thing. So if you check in this particular case, if it acts on A itself, the second term just cancels out because it's something like commutator of AI with AI, which is 0. Okay, and so then that's the equation that we want to give meaning of, right? And so we want to give a meaning to this stochastic PD, which we saw is of the form basically Laplacian of A plus some bilinear term in the derivative of A and A itself, plus a trilinear term just in A, local, and then space-time white noise. And we saw that just by power counting the regularity, right? So you can apply the whole sort of regularity structure machinery to this equation as long as the dimension is less than 4, because it becomes critical in dimension 4 and the machinery doesn't apply anymore. As long as you're in dimension less than 4, the machinery applies, and you get a solution, and the solution is in C, what is it, 2 minus D over 2 or something like that, right? Minus, always minus a little bit, say minus kappa or minus delta if you want for an arbitrarily small delta. So in dimension 2, it's just about not a function. In dimension 3, it's basically a distribution of regularity minus a half, or slightly below minus a half. And so that's roughly where we got to on Tuesday. And then what I mentioned is that, well, this is not great because, right, so here what it really means is that, right, the A is really an, so in components, you have AIs with I going from 1 to D, and each of these guys is sort of this guy with values in the Lie algebra of the structure group of your Young-Mills theory. And then I mentioned, well, that this is really not great because you want to interpret these things as connections, and the point of a connection is to actually determine horizontal lifts, right? And so, the horizontal lift is important to compute well. Like the natural observables of the theory are these Wilson loop observables that are obtained by basically just taking the horizontal lift of a curve and seeing by how much it moves sort of in the fiber by the time you've gone around the curve. And so you would like to somehow use these kind of connections in order to do like horizontal lifts along curves. But if you have an arbitrary distribution of negative order, well, there's just no way of restricting it to a curve, right? Because, for example, if you actually fix a curve, right, say in 2 dimensions, you fix yourself a curve, or say in 3 dimensions when you're just below a half here, right? So if you fix a curve and then you look at the function, which is simply 1 over square root of the distance to the curve, then that function belongs to this space, okay? But then obviously you cannot restrict that function to the curve because it's, you know, it's not even defined on the curve, right? So, and of course you can do that with, you know, like a superposition of a bunch of curves that are dense in the whole thing, and so it blows up everywhere at the same time. So clearly arbitrary elements of that space just cannot be restricted to curves. And therefore, there's no notion of holonomy or anything that's associated to a guy like that. Right? So we'd like to argue that actually you can solve this equation in a space that's better than that. In particular, that's kind of good enough so that holonomies or stuff like that makes sense, so that you have sort of notions of gauge invariant observables. And so here things start to become more dimension dependent in the sense that we have a much better handle on what we can do in 2 dimensions than in 3 dimensions, okay? And so I want to mostly discuss the and you see it's sort of clear in 2 dimensions, here you're just borderline not being a function, right? I mean, you're sort of 2 minus d is 0, and so you're just somehow in c minus delta for every delta, so you're kind of almost a function. Whereas in 3 dimensions, you're genuinely a distribution that's sort of like a half a derivative worse than any function. And so it's clearly going to be more problematic. So I'm going to mostly focus on the case of dimension 2, right? So from now on, until I say otherwise, we fix the dimension to be 2. And okay, so we want some kind of notion. Right, so we want a state space which is big enough so that it has a chance of containing solutions to this guy, and small enough so that elements of it have the sort of properties that you would like connections to have somehow, right? First, so in order to contain solutions to this guy, basically it's enough to contain solutions to the linear equation, right? Because what you can actually show is that if I write, say, Z for just the solution to the linear equation, and that one I don't need any theory to make sense of it, right? It's a linear equation. The solution to that makes sense for any distribution here, no problem. You just convolve with the heat kernel. So if I take the solution to this equation, then it turns out that one knows actually better. One knows that A minus Z belongs to C. Well, now it depends on the dimension, okay? But in dimension 2, this belongs to almost C1, as far as I remember. Wait a second. So you have, well, the worst case, you see, if A belongs to almost C0, then you expect this guy to be of regularity essentially -1. And then by the time you hit it with the heat kernel, you end up with something which is +1. This one is even better because it's basically regularity 0. So you hit it with the heat kernel, you get regularity 2 almost. So this here in dimension 2, you expect it to be in C1 minus delta. So that's in dimension 2. In dimension 3, it's worse, because even that difference is not a function. Okay, but in dimension 2, this is a function which is almost Lipschitz continuous. And so if your state space, is a linear space, and you know that it contains all C1 functions, or all, if you want, forms so that each component is a C1 function, then I really just need to be big enough to contain solutions to this guy, right? Because if it contains that guy, then it's also going to contain A, as long as it contains all of these guys, and it's stable under addition, right? If it's a vector space. And in dimension 2, it is going to be a vector space. Okay, so we want something like connections, some notion of connections which is sufficiently irregular so that it contains the typical samples of that guy, which for fixed time, that guy looks like a free field. Okay, so that's a standard calculation. Well, I mean, you can sort of easily imagine, right? I mean, if I have any linear operator here, the invariant measure of that guy is just the Gaussian measure that has as its covariance the Green's function of that linear operator. And so here it's the Laplacian, so it has the covariance, the Green's function of the Laplacian as covariance, so it's a free field. So this guy at fixed time is basically a free field. That means that the solution to this equation at fixed time basically look like a free field. So we want some sort of notion of distributional connection that's sufficiently weak in order to contain things that look like a free field in each of their components. Okay, so that's what we want. So say distributional connections. And now, what's the natural thing to do? So here we view things as actual distribution. And an actual distribution is basically the dual of a space of smooth test functions, right? So what you can do with distributions is you can test them against test functions. But that's not actually the natural thing that you want to do with a connection, right? The natural thing you want to do with a connection is integrate it along a line, right? Or actually even if we interpret this as a form, right, the natural thing that you use one forms for is to do line integrals, right? That's what one forms are designed for, right? So the thing that you do with one forms is you give yourself a line or something, and you integrate it along this line. Okay, so that's the kind of things you want to do with one forms. You don't want to somehow take the components in a coordinate chart and test them against the test function, because that doesn't really have a meaning for a one form, right? And so then the natural idea is to say, well, I do the same sort of thing as what I do with distributions, right? So distributions are a generalization of functions where I simply postulate what's the answer when I test it against any test function without knowing a priori that there exists a function which has the property that, integrated against the test function gives me these numbers. And so here I can do the same thing, which is that I view my distributional one form as basically a map from arrows, right? So I want I interpret it as a map from arrows into R, well, actually into G, because it's a G-valued one form, right? And what's an arrow? Well, an arrow is that, right? So an arrow is a is a starting point and an end point, or it's a starting point and a vector, right? That's an arrow. So an arrow, say L, I write it as xv, where x is that point, and v is the vector that gives you the arrow. Okay, so it's not just a vector, it's a vector that's also based at a point, right? And so I view A as simply a map from arrows to R, which has the property, so there are some arrows that can be composed, right, in the sense that the arrow xv and the arrow x plus v lambda v, right? So that's naturally given by the arrow x 1 plus lambda v, right? So if I have this arrow and then have another arrow that starts at this point and points in the same direction, right? Then I can compose these two arrows and I get another arrow which starts from the same point here and which has the length which is the sum of the two, right? So I can compose certain arrows, not many of them, but some of them can be composed. And now I want to interpret this guy, right? So I just have a map from arrows into the real or into G, which has the property that A of L union L bar is equal to A of L plus A of L bar for L and L bar that can be composed in this sense, okay? And the way you should interpret this, right, is that A of L, by definition, you should interpret it as the integral of A, of the one form A, along that piece of line segment, right, which is just the piece of line segment that is given by the arrow, which means, you know, I take the integral, say, from 0 to 1, right? Integrating one forms along curves is independent of the parametrization of the curve, right? So I can just parametrize that arrow by starting here at time 0, getting here at time 1. And so I write it as an integral from 0 to 1 of ax plus tv. So that's going along the arrow from the point x to the point x plus v. And then I test it against v, and then I just do dt. Right? So that's the integral of a against my curve. So of course, if I'm given a one form, then I can define a collection of numbers in this way, and they will have that property, right? So if I'm given a one form, then that determines such a map, right? Which has furthermore this additional property. But now I want to sort of, like for distributions, I go the other way around, and I just say, well, I fix such a map, and then that's it. That's my object. And then I want to somehow interpret it as a one form. And just like for distributions, I want to just be guided, if you want, by this correspondence in the way I'm going to define things. Okay, like for distributions, you can define, you know, what does it mean to take the derivative of a distribution or blah, blah, blah. And the way you do it, you always think of the distribution tested against the test function as being integral of the function against the test function. And then you say, oh, what would it be if you take the derivative? So you do an integration by parts, blah, blah, blah. And then you just define it like that, okay? So exactly the same idea. So we say we define a distributional connection is just a map like this. And then whenever we want to define some kind of operation on connection, we see, well, you know, what would the operation do here, and then try to use this identity to try to guess what would be the correct definition here. Okay, so that's the and so okay, so now what do we want? We want well, okay, so the first thing is we want some sort of reasonable space, right? So that would be like the analog of the space of all distributions, right? Okay, that's not a nice space. Okay, and so similarly, in the case of distributions, we had this notion of sort of distributions of negative Hölder regularity, where you say, oh, you test against the test function, and then you want some sort of quantitative bound about, you know, how big is the answer allowed to be if the test function looks a bit like a delta function or something like that. Okay, so here, same thing. You want to impose some kind of quantitative bounds on that. And so what's the kind of, so say quantitative bounds? So what's the kind of bounds you want to impose? Well, first, you want to impose that these things, these integrals, are not too big if the arrow is not too long, right? So given an arrow L, I'm going to write L as being just, that's just the length of the arrow. Okay, absolute value of L is just the length of the arrow. And so it's natural to impose something of the form, A of L should be bounded by a constant times the length of the arrow to, say, some exponent alpha. Okay, so of some kind of regularity. Now that exponent, in some sense, differs by 1 from the Hölder regularity of the components, at least morally, right? Because if the A was a connection was a one form in the usual sense, and the components are, say, just continuous functions, so they have regularity 0, then what does it mean? So you just take a bounded continuous function here and you integrate it along the arrow. The thing that you're going to get is going to be bounded by the length of the arrow, right? So if the A was an actual connection with continuous components, then you would have a bound like that with alpha equal 1. Okay? And so since we want distributional connections, well, we want bounds like that, but for alpha a bit less than 1. And so the alphas that are going to be relevant for us are going to be, say, between 0 and 1. Actually, we're going to see that 2/3 is already special, and so you actually want it basically to be between 2/3 and 1. But okay, for the moment, the definition certainly makes sense between 0 and 1. But that's, of course, if we only impose this, that's really not great, right? Because, for example, if you integrate your one form along this piece of line, well, or you could integrate it along this piece of line, which is just next to it. If it's anywhere near reasonably behaved, the two integrals should be close to each other, right? If we only impose that, that says absolutely nothing. Right? So that integral could be completely different from that one. And so if you have only a bound like this, in particular, there's no chance of having a reasonable definition of, the integral of the form A along a curve, because the way you would want to do it is you would want to somehow approximate your curve by little pieces of straight line and then show that that integral converges if you make your pieces of straight line shorter and shorter. But if you have absolutely no bound on how this changes, if you take two pieces of straight line that are really, really close to each other, well, then you have no chance of having any sort of convergence, right? So you have no chance of being able to define the integral of A along a curve in any way that's somehow regular as a function of the curve, right? So you want some additional regularity. And so what's the natural thing to impose? Well, one natural thing to impose, I claim, is to actually look at the integral along a triangle. Okay, so take a triangle. And so a triangle is just that, right? So it's 3 elements of this space with the property that, the end of each of them is equal to the beginning of the next one in circular order, okay? And so say I take a triangle, I call it P, and then actually let me write, so if I have this, right, so say here I have an L1, L2, L3, then I would write A of dP. It's just a shorthand for A of L1 plus A of L2 plus A of L3, right? So that's just, okay, it's self-explanatory, right? So somehow the integral of the one form along the boundary of my triangle is just given by, the sum of the integrals along the 3 faces. So now I claim that it's not a bad idea to impose, furthermore, a bound of this type here, alpha over 2, where this guy is the area of the triangle, right? So that's my... Okay, so the absolute value, if you want, of P. So P is a triangle. Absolute value of P denotes the area of the triangle. Del P denotes the outline of the triangle, which is really just 3 arrows. Okay. I claim it's not a bad idea to impose a bound like this. So first, why alpha over 2? It's kind of natural because here we have a bound on A that scales like a length to the power alpha. This is an area which is like a length square, and so this whole thing is really, again, a length to the power alpha. Okay, so it has somehow the same units, if you want. It's also natural because these two bounds are sort of compatible in the sense that if I take a triangle that actually looks like this, in the sense that all 3 angles are somehow, not too far from 0 and not too far from 180 degrees, so it's sort of non-degenerate, right? Then the typical length of a face of the triangle is about, so the area of my triangle is about any of the 3 lengths squared, right? The 3 lengths are all 3 about the same length, and the area is just the square of any of them. And then in that case, well, this bound basically just follows from this one. Right? So if I take, for example, equilateral triangle, the bound of this bound for equilateral triangle just follows from this bound. Right? Okay. But it actually tells me, where it tells me more is if I take very flat triangles. Right? So if I have a triangle, so this bound is really interesting if I take that sort of triangle. Right? So if I have a triangle that's very flat, then this length can be quite big, but the area can be very small. Right? So I could have a triangle like that where each of these lengths is about 1, but the thickness here is epsilon. Right? And then from here, I just get a bound of order 1, but from here, I get a bound of order epsilon to the alpha over 2. Right? So for very flat triangles, this really tells you genuinely more than this. Okay, for sort of fat triangles, this guy is implied by this one, but for very skinny triangles, this guy does not follow from this one. Okay, and that's of course where this guy is important, is interesting because, so for example, think of a skinny triangle that looks like this, right? And so then what does this bound tell me? It really tells me that A of, right? So if I have an L like that, and then an L bar like that, and say L and L bar start from the same point, and they point in slightly different directions, right? Then this is very small, say epsilon. Okay. And then what is A delta P? If I look at this triangle, A delta P is equal to A of L, right? In this example, this would be A of L minus A of L bar. Oh, yeah, so because here, right? So here in particular, one consequence of this is that if I look at the reversed arrow where the, starting point becomes the end point and the end point becomes the starting point, that just changes the sign of that thing, right? Because the 0 arrow would always be mapped to 0 automatically, the arrow of 0 length, right? And here, if you want, lambda could be -1, right? And so then if I can compose an arrow with the arrow that goes backwards, and then I get a 0 arrow, 0 length arrow. And so that tells you that A applied to the forward arrow has to be equal to minus A applied to the backward arrow, okay? So here, if I turn this into a triangle, I have to change the sign of one of the 2 arrows. That changes the sign of the A. And then I have that little piece, which is something which is of order epsilon to the alpha. And we then know that this is less than epsilon to the alpha over 2. And so then in particular, it tells me that A of L minus A of L bar is less than epsilon to the alpha over 2, right? So it tells me if I have two arrows that are sort of of order 1 length, but that actually differ by only order epsilon, then the A's differ by something small. Okay, so that gives me some kind of regularity as a function of the arrow. And here, okay, so here I've done the arguments where I change the endpoint. Of course, you can do the same argument where you change the starting point by just reversing the arrows. And therefore, just by composing the argument twice, you can change both the starting and the endpoint, right? Of course, here I have a bound. I already wrote P. P stands for polygon. I only talked about triangles, but you could actually now replace triangle by quadrilaterals or pentagons or something. And exactly the same bound follows from this bound here, because of course, if you have a quadrilateral, you can just chop it up into two triangles, and the bit where you've cut it cancels out, because it comes up one with a plus sign, one with a minus sign, and then you just add up the bounds for the two triangles, and you get something of the same order, just with a factor 2. Okay. So that bound then automatically holds for polygons of arbitrary length, but the constant would depend on the number of sides of your polygon. Okay, okay. Are there any questions? Yeah. Oh, okay. Huh? Yeah. So we work in dimension 2. Well, it doesn't make any difference, right? R2 or yeah. So if you tell yes. Yeah, torus or R2, but so whether it's torus or R2 makes no difference. But yeah, so here I'm on flat space. But since we're going to see in a second that this condition then implies that you can actually make sense of A integrated along smooth curves, that means that actually, if instead of having a flat space, you had a manifold, well, you could take this definition in a given coordinate chart, and then you would have a theorem that says that the spaces are equivalent if you take a different coordinate chart. And so, okay, and there was another, okay, that was the same question. Sorry, I can't hear you. No, the Lie group here doesn't matter. You see, so here it takes values in the Lie algebra. Now, of course, the Lie algebra is a vector space. Yeah, okay, holonomies are going to show up in a second. So for the moment, there's no holonomy. Right? But when but we're not going to assume that G is commutative, because that, yeah. Okay, any more questions? No. Okay. So, right. Okay, so that was pretty natural, right? So it's some sort of natural notion of distributional one forms. And so now we would like to know, well, there's two things we would like to know, right? The first one is we would like to show that these guys do what one forms are supposed to do. So far, you just postulate what's the value of the integral against a piece of straight line. But what you'd really want to be able to do is integrate the one form along an arbitrary curve. Okay, so that's the first thing we want to do now. And then we want to, once we know how to do that, then we can discuss holonomies. Then once we know that we can define holonomies, well, then we want to argue that actually solutions to this equation do belong to such a space. And so the claim will be, so I'm going to define, so let me call this space, say, omega alpha. So omega alpha is just the set of all A's like that, which satisfy these two bounds. Okay. So now I want to define the integral of A against an arbitrary curve. So, so I'm going to assume I have a curve which belongs to C beta. And I'm going to always assume here that beta is bigger than 1. Well, okay, I'm always going to assume that beta is somewhere between 1 and 2. Okay, in the sense that if it's allowed to be infinity, obviously, right? I mean, a C infinity curve is C2 in particular. But it's just that if it's better than C2, that doesn't help me more somehow. And if it's less regular than C1, then that's just not good enough for what we want to do. Okay, so we want our curves to be at least Lipschitz and, you know, potentially like C2 regular or something like that. Okay. Now, if you have a curve like this, right, so say a gamma like that. Now, of course, you know, when I draw a curve like that, in principle, drawing a curve is sufficient in order to determine what the integral of a one form is along it. It's not sufficient in order to determine that, right? Because this is not just a drawing of a curve, it's a parametrized curve. Okay. And so, of course, the same curve can be parametrized in different ways, and in some ways it might be C beta, and in some ways it might not be. And so you just choose the best parametrization if you want. So, for example, if you take a square, you would think that this is not very smooth because it has corners, but it actually has parametrization for which it's C infinity. Okay. So in this sense, a square is C infinity and not just Lipschitz. Right? You might think a square is only Lipschitz, but it's actually C infinity. On the other hand, if you take a staircase like this, now I just told you it's C infinity, which is true. But now if you take that staircase and you make the stairs smaller and smaller, and you would like to say that, you know, it approximates actually just a straight line like that, that's not going to be approximated in any of those norms, right? So that would be true only for betas less than 1. Okay, so in particular, so a staircase does not converge to a diagonal in any of these topologies. Okay, so that's just to give you some kind of idea. So like the curves are allowed to have corners, right? Because the reason is, you see, like if you want to go think of drawing the square as a projection, you draw a curve in 3 dimensions, and then you project it down, right? Removing a component from a curve doesn't make it less regular, right? If a curve is C infinity as a curve in R3, then if I just forget about the third component, it's still going to be C infinity, right? It's not going to magically make the other 2 components less smooth. And of course, it's quite easy to actually find a smooth curve in 3-dimensional space, which is such that when I project it down, it becomes a square, right? Because all I have to do is at the corners, I kind of sort of go vertically. Right? You see what I mean? Okay. Okay. Right, so that's the sort of curves that we want to integrate things against. So what's the property we're going to use of these C beta curves, okay, is that if I take 3 times, so say S, U, and T, which starts to smell a bit like a sewing lemma. And now I look at the triangle, right? So I look at sort of this thing. So the length here, right? So that's going to be basically of order T minus S. Right? So here, in some sense, whether the curve is Lipschitz or C beta doesn't really help. Right? I mean, it's basically going to be of order T minus F. If it was C alpha, then of course it would be even less. If it was C beta for beta less than 1, then it would be even, then it would be T minus S to the beta. But since beta is bigger than 1, basically the length of this side is going to be about T minus S. But now what does the beta, where does the beta between 1 and 2 help? Well, it tells me that the tangent vector to the curve cannot move by too much during that time t minus s, right? Because the tangent vector itself is c beta, okay? And so if you think about it a bit, what it tells you is that sort of that triangle has to be very flat, right? Because if the tangent vector doesn't move at all, then the triangle would actually have to be completely degenerate and have area 0, okay? And if the tangent vector moves a little bit, well, it makes that triangle somehow very flat. And how flat is it? Well, basically the height of the triangle here will be less than t minus s to the beta, okay, for beta between 1 and 2. And that's why I say between 1 and 2, right? Because even if it's C infinity, it's not going to be better than t minus s square here, okay? But in general, it's going to be, for a smooth curve, it's going to be t minus s square. And for a C beta curve, it's going to be t minus s to the beta, okay, for beta between 1 and 2. So that tells me that if I have a C beta curve, and I look at a little triangle like this, the area of the triangle is going to be bounded by about t minus s to the 1 plus beta, right? Okay. So now we take such a curve and we want to somehow define the integral of A along the curve. Okay. And so now how do we do that? Well, we define AST. Well, so first let me define an arrow. So I have a curve gamma, right, from say 0, 1 into my two-dimensional, well, let me write R2 or two-dimensional torus, makes no difference. Okay, so I have my curve, which is C beta. Then I'm going to write gamma ST for the arrow, which starts at gamma S and with direction, gamma T minus gamma S. Okay. And now I say, well, AST is defined as being A of gamma ST. Okay, so now that's a function of two parameters with values in Gothic G. Okay. And this guy is, right, so what's that guy? That's the integral of my one form along this line, if you want, just along the chord that goes from gamma S to gamma T. Now I claim that if beta is good enough and alpha is bigger than 2/3, and that's where the 2/3 shows up, I claim that this guy is actually a good guy to be stuck into the Sewing lemma. And so why is this a good guy to be stuck into the Sewing lemma? Well, we want to show that if you have an interval ST, right, we take an S and a T, now you take a U in between, and we want to say that AST is not too far from ASU plus AUT, right? And then, of course, that's how we want to define the integral along the curve. You sort of take chords, and then you sort of make the chords smaller and smaller, and you want to show that, this guy converges. And that's exactly what the Sewing lemma does, right? It's exactly doing something like this. You have sort of function of two parameters, which is not quite additive, and then you want to turn it into something additive by looking at it on smaller and smaller pieces, okay? So that's exactly what you want to do. And so we just need to check that the assumptions of the Sewing lemma are satisfied. But now, AST minus ASU minus AUT, what is that? That's just A of, say, gamma SUT, where gamma SUT is precisely that triangle, right? Because these guys come with a minus sign, and the other one comes with a plus sign, and that means that you go forward here, and then you go backward here, and you go backward here. Right? So that's exactly A applied to this triangle. And so by definition, this is bounded by the area of that triangle, the SUT, to the power alpha over 2. But the area of that triangle, I just argued, is t minus s to the 1 plus beta. Right? So here it's bounded by t minus s to the 1 plus beta times alpha over 2. Okay? And so in order to apply the Sewing lemma, all I have to guarantee is that 1 plus beta times alpha over 2 is bigger than 1. Right? That's the condition for the Sewing lemma, which means that beta needs to be bigger than 2 over alpha minus 1. Or if I want to view it as a condition on alpha, I need alpha to be bigger than 2 over 1 plus beta. Right? And so you see, here you see why 2/3 now show up, is that beta equal 2, which is the largest possible value of beta, because you can never go beyond 2, even if the curve is T infinity. Here you just get T minus S squared. You never get anything better than that. Right? So if beta is equal to, alpha has to be bigger than 2/3. Okay? And if beta is smaller, that means that the alpha has to be bigger, okay, as usual. Right? So in reality here, we really want kind of 2/3, because if it's less than 2/3, then we can't actually extend it to curves. Okay, but so now I can just apply, right? I can apply the Sewing lemma. And so the Sewing lemma now tells me that there's a function AT, so that AST is equal to AT minus AS. And then and then that function AT is interpreted as the integral of the one form A along the curve gamma up to point gamma t. Right? And of course, it's the correct interpretation, because like if the curve is a straight line, then of course it's equal to that. And if the form is smooth, then it's equal to that, and so on. Right? So you can check you can do all the reality checks that tell you that this is consistent. Right? Okay. So, right, so the upshot here is that provided that this condition is satisfied, these distributional one forms in this space omega alpha, can actually be integrated along curves of regularity beta. Okay? So in particular, if alpha is bigger than 2/3, they can be integrated against smooth curves. Okay. But now we also see that, again, as a consequence of the Sewing lemma, well, AST itself is of course bounded by T minus S to the alpha, right? Because that's just this bound here. And the fact that the length of this arrow is bounded by T minus S. And so the Sewing lemma also in particular tells us that the integral of my one form along a sort of piece of smooth line is going to be bounded by the length of that line to the power alpha. Okay. So if we just look at the integral along the curve as a function of the parameter of the curve, we're going to get a C alpha function. Okay. So that's also why omega alpha. Okay. So now alpha is going to be large. So we're going to take alpha close to 1, right? Because you remember, we think of that alpha as being basically this plus 1, this exponent plus 1. And so since we expect in 2 dimension to have this guy, the components here, to belong to just C minus delta for arbitrary delta, we actually expect the guy to belong to omega 1. If it belongs to that space, then ideally it should belong to the space omega 1 minus delta for arbitrary delta. So almost omega 1. Right? So it should be almost in this space with alpha equal 1. That means that you should be able to restrict So alpha equal 1. Here it gives me beta bigger than 1, right? So you should be able to restrict to basically any curves that are a bit better than Lipschitz. And the restriction to such a curve should give you a function which is C alpha for alpha very close to 1. Okay? Now, since the restriction to a curve is actually C alpha, so the integral along the curve is C alpha, well, so now defining holonomies is actually not a problem. Because if you write down, you know, what defining the holonomy actually entails, it entails sort of solving an ODE, and it entails sort of solving an ODE that's driven by this form A, right? It's something like a, you know, I don't know, dg equal to G inverse times dA or something like that, right? Or dA times G inverse, like some ODE of that type, right? Which is nonlinear, but it's driven by A. And so now you can view this just as a Young differential equation, right? So it's like a Young ODE, as you've seen in the lectures last week. And so then that makes perfect sense as long as the regularity of the driver is bigger than 1/2. Well, and here it's going to be close to 1 and certainly bigger than 2/3 because otherwise we can't even do this restriction anyway. And so defining holonomies is not a problem. All right, so we can use this to define holonomies. So in that sense, this is a nice space, right? So you have something, so you have some kind of generalization of one forms, but they're still good enough so you can restrict them to Boltzmann arbitrary curves, you can compute holonomies, you can do anything with them that you want to do with usual one forms. So now one thing that you would want to, okay, it's only half an hour left, right? So here, so we have that space omega alpha. Actually, the space we really look at, we look at a space which is a little bit smaller. So one problem with this space, as I've defined, is that it's not separable for the same reason as, you know, like C alpha is not separable. You can fix that easily by taking closure of smooth functions under these norms. And basically the only thing that happens then is that in all these definitions, the coefficients in front go to 0 as the length of these guys go to 0 somehow, right? So like if you take small triangles with small diameter or segments with very small length, then you would want the constant in front actually to go to 0. And then that's the space that you get when you take smooth guys and you complete under that norm. And then that space is also separable. Right. So I'm going to ignore that subtlety from now on. But that's just then at some point I'm going to make a claim that something is Polish. And then of course for that you need separability. And so, okay. So now there's one other thing we wanted, right? So now we have a sort of reasonable space of these distributional one forms. It's not very difficult to check that the free field can actually be realized by, like, if you take a guy so that each component is a free field, then there is a version of it that, you know, if you want, it can naturally be realized as an object like this, okay? The reason is, well, so first maybe you know that sort of the two-dimensional free field can be restricted to horizontal, to sort of straight lines. It can certainly be restricted to circles because that's what's used a lot in sort of like in the stuff a la Sheffield, Duplantier and company. So you can also restrict it to straight lines. I can show you sort of a relatively simple calculation that shows you, or at least argues, why the free field would sort of satisfy a bound like this. Right, so if A behaves like a GFF, again in dimension 2, okay, it's always dimension 2. So if A, so the claim is that if A is a GFF, then A belongs to omega alpha for every alpha strictly less than 1. Okay, so that's the somewhat loose formulation of a theorem. And if you want the precise formulation is you take the GFF, you hit it with a modifier so it becomes smooth. Then, of course, you can lift it to an element in omega alpha because it's just a smooth guy. And then you remove the modifier and it converges to a limit in all of these omega alphas, and the limit doesn't depend on the modifier. Okay, so it's in that sense that it belongs to that. So now I'm going to ignore this whole modifier thing. I just do a formal calculation, and then you justify the formal calculation by doing the whole modifier business. Okay, and so how do I check this? Well, I basically want to apply some kind of Kolmogorov criteria. Okay, and the claim is that there's a Kolmogorov criteria here, which is that if you have a bunch of random variables, right? So if you're just given a bunch of random variables A of L, okay, so you just have random variables indexed by these arrows, and assume that this holds in LP, right? So in the sense that the LP norm of this guy is bounded, right? The LP norm in the sense of pth root of the expectation of the pth moment. So the LP norm of this guy is bounded by that, the LP norm of that guy is bounded by that, uniformly over the L's. Then there's a Kolmogorov criteria that tells you that then A has a version that belongs to these spaces, and you lose 16 over P or something like that. Okay, and so if P is arbitrary, you lose an arbitrarily small amount, just in the same way as the usual Kolmogorov criteria. Okay, so the usual Kolmogorov is if you want to check that something is Hölder, you basically check that the LP norm of the increment is bounded by T minus S to the H, and then you know that it belongs to, it has a version which is almost surely belongs to Hölder space, which is not H Hölder, but you lose a little bit, and so you lose dimension over P or something like that in the usual Kolmogorov criteria. Okay, and of course, since here everything is Gaussian, that means that P is arbitrarily big. So I make calculations for second moment, but if you bound the second moment, then you automatically bound every moment because of equivalence of moments. Okay, so if I look at something like expectation of A of L square, so what is it? Well, basically, I just look at this formal expression, right, and I square it, right, so I just square this expression, and I brutally sort of, take the expectation, pretend that everything makes sense, and check that I get an answer which is of the order that I want. And so here I get, sort of integral 0, 1, expectation of a sort of x plus tv of v, a x plus sv of v ds dt. And then here you just get, a correlation of the free field at 2 points. The two-dimensional free field is log correlated, so the correlation is just the difference between the 2 points. Here, the difference between the 2 points is t minus s times v, right? So this expectation here just behaves like log of t minus sv, okay? And then you just integrate the log over, 2 lines, and you have a v that comes out. And so you find immediately that this is of order v squared. So you get the v square, which is exactly that bound with alpha equal 1. Okay. The area bound appears to be slightly more tricky. So if you brutally do it like this, it becomes super messy. But there's a trick, right? Because you're integrating, you're taking a vector field, if you want, formally, which you integrate over along a curve, and you can use Stokes' theorem, right? So that's the same as actually integrating the curl over the triangle, right? So this guy, instead of writing it as a line integral along the triangle, I can actually write it as a two-dimensional integral of the curl on the triangle, right? So then what do I get? Right, so the A of dp, I write it as an integral over P of the curl of A, dx. Okay, so that's just line integral, that's just Stokes' theorem, okay? And so expectation of this guy square is the expectation of this guy square, right? And so then what does that give me? So the curl of A, so the covariance of the covariance of A is is the Green's function of the Laplacian, right? So formally, it's the inverse of the Laplacian. And the curl is just a one-dimensional differential operator. Okay? And so what I get, so if I say, you know, I look at one of the components of the curl, right? So I have sort of diaj, so say d1a2, and there's a minus d2a1. And I forget about, I just bound them separately, okay? If I can bound one of them, I can bound the sum. So I just look at the expectation of that integral of d1a2. Then what is that equal to, right? I can write this as the expectation of a double integral of the indicator function of the triangle on x, indicator function of the triangle on y, and then I have a d1 a of x, d1 a of y, and then I have a dx dy, okay? So I get this. And then I find that the covariance of the A is the Green's function of the Laplacian, which I can formally write as delta inverse hitting delta x minus y, and then I have a d1 I have sort of a, okay, so here the 1 hits the first component of x, here it hits the first component of y, but then of course here x and y show up in the same way, so it's just a sort of derivative of first component square. And then I can use the fact that this guy is actually a bounded operator in L2, and I end up with something that just shows up. Right? So in the end, I end up with just the L2 norm of the, actually I think it shows up without the square because of that delta function, right? So at the end of the day, okay, I might confuse myself, that's an exercise to kind of, to do that calculation properly, and you just find the L2 norm of the indicator function of the triangle, which is really just the square root of the area of the triangle, right? Okay, so you find exactly the bound that you want here with alpha equal to 1 again. Oh no, actually here it does show up with, sorry, okay, it does show up with a square, and therefore without the square root, but here there's a square as well, okay, and therefore you do want the area that shows up and not the area, not the square root, okay? So you can apply Kolmogorov, and then that tells you that this guy does really belong to these spaces, okay? So you have a chance that the solution belongs to that space. And so now the property, but the other property that we wanted of this space is that, right, so now we have holonomies, so Wilson loop observables are well defined. The free field can be realized as a random element of that space of distributional connections. Therefore, you'd expect that the solution to this equation can be realized as a process with values in that space, okay, and you can prove that. Now, the final piece of the puzzle here for the state space is that we wanted, right, at the end of the day, we want to take the quotient by the gauge group, right, because we really want to view the process not as a process on connections, but as a process on equivalence classes of connections. Okay, so we want to quotient out that space by the action of the gauge group. So, and remember, I made quite a big fuss a few times already about the fact that if you want to quotient the space of connections by that gauge group, you really have to be quite careful about matching the topologies between the two, okay? And so I claim that this space omega alpha, furthermore, actually has the very nice property that its topology really matches the topology of just C alpha functions with values in the structure group, okay? So now I write curly G alpha to be the G's from, say, two-dimensional torus into G, such that G is in C alpha. And again, I really mean closure of smooth functions under that norm for the same reason as before, okay, this whole separability business. Okay, but basically just alpha holder functions. And now, there's two things. Now I claim that this topology is really very nicely compatible with that one. And that's true in two directions. So first, I claim that if you have a guy in that gauge group, then there's a natural action of it on these distributional connections in such a way that the new guy again belongs to omega alpha. Okay, so that's the first thing. So that goes sort of in one direction. That's compatibility in some sense in one direction. But then, okay, so claim. So first, if I take G in G alpha and I take A in omega alpha, then G dot A or AG belongs again to omega alpha, and in which sense, well, okay, so first you can say, well, you know, these guys, both of them are closures of smooth guys, so I can just take any smooth guy approximating that, any smooth guy approximating that, then it's clear what this means, and then the claim is that if these two guys converge, then that guy converges, okay? So in that sense. You can, of course, you can have also a slightly more intrinsic definition, and so one way, so if I write, yeah, maybe I don't really want to write that, okay. I mean, you can just, the AG, right, applied to L, you can basically guess a formula for it, right? Because you say, well, okay, so it is somehow this integral, and now what I want to do is I want to sort of put a GG inverse here, and then I want to actually interpret this as simply an integral of a reasonably regular function against my one form, right? And then again, these integrals just make sense as Young integrals. Okay. And there's a GDG inverse, there's a DGG inverse term that showed up, and then again, that's just the one form that you integrate along the curve L. And then again, it makes perfect sense as a Young integral, okay? Because alpha is bigger than a half, alpha is going to be very close to 1. And so integrating something like DGG inverse makes perfect sense as a Young integral, okay? So this guy, it's not difficult to make sense just by Young integration, you know, and then in the same sense as usual, so the Young integration immediately somehow gives you a bound like this, And then you just have to work a little bit more for a bound like that, okay? But the claim is that it's not terribly difficult to do that, and somehow the exponents here match up in the right way, okay? So that goes in one direction. But now, if you want the quotient space to be nice, you also want some sort of compatibility in the other direction, right? So the sort of thing that you're fighting against is, well, so for starters, if you look at all of these guys, you look at the collection of all the AGs for G and G alpha, for example, you don't know a priori whether this is a closed set. Right? It would be really nice if this was a closed set, right? For example. And I claim that it is. And the thing that really makes it work is that there's a kind of a bound that goes the other direction. Okay, so here you obviously get a bound on the alpha norm of AG in terms of the alpha norm of A and the alpha norm of G. Okay, by just keeping track of, you know, all the stuff that appears in your Young integration, you get a bound on that guy in terms of these two norms. The claim is that it kind of goes the other way around also. Okay? And so the bound that goes the other way around is that if you can get a bound on the Hölder norm of G, knowing bound on the Hölder norm of A, and the bound on the Hölder norm of AG. Okay, so the claim is that if you take two guys that are equivalent, so two guys that are in the same gauge orbit, then I can get a bound on the size of the gauge transformation that maps one into the other one, which is nicely uniform in terms of just the bounds of the two guys. Right, so what this tells you is that if you see, what's the sort of things where this is not true at all, right? So say you have A here, and then you have your orbit, right? So you have your AGs. Now, you could imagine situations where this thing sort of folds back onto itself. Right, so you could easily imagine situations like this, where in some sense you take a very large G, so you move out in the Gs, but when you look at AG, it sort of folds back onto itself, even though the G was very large. Right? There's no reason a priori why this shouldn't happen. Right? So for example, if I take at the action of R onto a two-dimensional torus, which is given by an irrational rotation, this is exactly what happens. Right? You start from a point, you move really far, but you keep on coming back, closer and closer by moving further and further away. And so you very much don't have a bound like that in that case, right? Because you can have two guys that are very close to each other, but that are given by the action of a very, very large G, right? And the claim here is that this cannot happen. If you take an A, which is over the order 1, and you take a G that's very large, then it kicks you out very far. Okay, so that's the claim. And this is really, right, so this is really crucial. This is really the crucial ingredient in order to show that the space of gauge orbits itself as a space is not sort of nicely well defined, because it tells you that the orbits don't look like that. They don't look too crazy, right? And actually proving this, I mean, once you dare to hope that you have a bound like this, is actually not difficult to prove. Right, so you can, because there's basically a formula. Sorry? Oh, it's not so much about being close to each other, but it's about yeah, so maybe I shouldn't have said close to each other. It's like close to the origin, right? So you could have, So the thing is, if both A and AG are not too big, right? If A and AG are both order 1, then it means that G has to be itself order 1. You cannot have a very large G that links two guys that are both order 1, if you want, right? That's what this tells you. Yeah. So that's not obvious, but you can deduce it's true. Yes, so it's true that the orbits are closed. So if you look at the set of AGs, right, for G and G alpha, and you can basically deduce it from that, but it's not completely immediate, right? So it's a bit of an argument, but this is also the main ingredient in the proof. Yeah. But yes, you can prove that the orbits are closed also. And so, let me see, how much time do I have? 13 minutes. Okay, so let me just say, yeah, okay. So this guy, basically the reason why a bound like this is true is because you have a formula of G in terms of, so if you fix a point X, and suppose that you know little g at X, and it's not too difficult to somehow guarantee that, like, at a fixed point, the little g is not allowed to be too, I mean, so there's no size, right? G takes values in a compact group, right? So like values at a point cannot be large because they take values in capital G. Capital G is compact, right? So the only reason why elements are large is because they sort of oscillate fast, right? So the only reason why elements here, why this norm can be large, it's just because, you know, G, the function little g could be very irregular as a function of X, right? But it's not about individual points becoming large because they take values in a compact set. So suppose you know G at some point X, some fixed point X, doesn't matter which one. And then if you want to know the value at any point Y, actually you take any curve gamma xy that connects X to Y, for example, the straight line, doesn't matter. And then you have a formula actually that, so let me write it down. It's I mean, once I give you the formula, you can actually just check that it's true somehow. And so the formula is that it's the holonomy of AG along gamma xy inverse times G of X times the holonomy of A along gamma xy. Okay, so it turns out that this, it's not very difficult to somehow see. So it's a good exercise to convince yourself that this formula is true. And then once you know that formula, well, it's, you know, it's not very difficult to actually check something like that, right? Because you just, you know, you move your y by a little bit, and so you just add to your curve a little segment here, and you have all these bounds about how big the holonomies are when you move along a little segment, and you have good alpha holder bounds on that stuff, right? And so it's not very difficult then to see that the G can only move by some sort of controlled alpha holder amount, right? Okay, so once we know this, the claim now is that, so the claim is that omega alpha over G alpha is a Polish space. Okay, so omega alpha is a perfectly nice Banach space. G alpha is a perfectly nice topological group. There is a, you know, quotient topology here. The claim is that you can find a metric, you know, that metrizes that topology, and the metric is complete. Right? So how do you do that? Well, you know, what's the way that you would want to define the metric? So say I write A for the set of all AGs. There's G in G alpha, right? So that's my equivalence class. And now you want some kind of metric that, say, D alpha between A and A bar, okay? So how would you define, so now that's two sets, okay? So they are just subsets of omega alpha. And of course, if you have a metric space, there's a very natural distance on subsets of the space, which is the Hausdorff distance, right? But, okay, Hausdorff distance may not be very nicely behaved because these sets are not compact, right? They're closed, but they're not compact. So the sort of problem that you have is if you simply, right, I would like to say that this is simply Hausdorff distance. The problem that you have is that, you know, your gauge, these things are infinite dimensional, right? They're sort of big, so typically your gauge orbits might look like this, right? So say maybe this is A, and now I have an A bar, which is very close, but it might look like that, right? And so that's A bar. And so here, you know, they are sort of two orbits where they are very close here. But then when you sort of go far out, if you act with a large element of G, then, you know, they might actually just separate pretty fast, right? So now here, if I look at the Hausdorff distance, it may well end up being infinite because you go far out, and then there might be that the closest point actually gets arbitrarily far. And so you want to somehow fix that problem, right? So you want to say, oh, it should really be Hausdorff distance, but Hausdorff distance in a way that mostly, you know, cares about what happens in here in some sort of bounded regions and doesn't really care about what happens out at infinity, okay? And so for that, the idea is what you do is you do you take the Hausdorff distance, but not with respect to, right? So on omega alpha, I have a norm, which is simply, you know, this, yeah, well, now I've erased that as like the smallest constants that appear in these two inequalities. So this guy has a norm, but now the idea is that I just stick a different metric onto that, which is equivalent to that norm. So it gives me the same topology, okay? But that metric would be much nicer in order to define the Hausdorff distance. So it will guarantee in particular that the Hausdorff distance is actually finite between any two guys. And so it will actually be Hausdorff distance with respect to, say, K alpha, and I'm going to define the metric K alpha now, right? So the idea is to say, well, I have that Banach space, and I basically want to turn that Banach space into some kind of teardrop. Okay, so what do I mean? So I want to make it have that shape. And so that, say, the origin is sort of somewhere down here, and these kind of guys here are sort of my spheres of large radius, right? So like that somehow, the set of A's, so that norm of A is equal to R for large R, right? And so then the idea is to say, so for large R, the kind of large spheres in my space, I kind of shrink them, right? But I shrink them in such a way that that distance here remains about R. Okay, so I don't really change. So the guys that are of size R, I keep them at distance about R from the origin, but I make those spheres, I shrink those spheres to something very small. So the diameter here is about 1 over R. Right? So the spheres of radius R, which have diameter R, I want to shrink them to having about diameter 1 over R instead. Okay? So how does that work? So I define K of A bar to be the norm of A minus norm of A bar plus 1 divided by the minimum between the norm of A and the norm of A bar plus 1. So here the brackets go like that. And then the whole thing multiplied by norm of A minus norm of A bar, well, norm of A minus A bar, minimum 1. Okay, so that works in any Banach space. So I just choose, you know, here it would be the omega alpha norm, but of course the construction works in any Banach space. First, that's not a distance, okay? That guy is not going to satisfy the triangle inequality, but it sort of almost satisfies it, and so you can just look at the distance that it generates, right? So you see the distance between 2 points is sort of the infimum over all intermediate points of the sum of these guys over that path, and then you find out that if your 2 points are not too crazy, there's actually not many intermediate points, and the thing that you get behaves pretty much the same way, okay? So I pretend that this is my distance. The distance is something which is basically equivalent to that. Okay, and you see that this has these properties, right? So if I take the A's, all the guys in the sphere of radius R, then that difference is 0. Here you have R, so you get a 1 over R here. Oh, I see, so okay, and here, right, and so here this is at most 1. Right? And so the distance between any two guys that are on the sphere of radius R is at most 1 over R. But on the other hand, if I look at the distance between a guy on that sphere and the origin, right, then here you get R divided by nothing, right? So the minimum here would be 0 plus 1. So here you get R plus 1 over R. So that would be R. And then that minimum 1 is still 1. Okay. So if you take so this distance is still R, but the diameter here is now about 1 over R. And the topology is clearly the same, right? So if I fix A, well, then this is just some sort of big number or so, either big or small, depending on what. And then for A bar close to A, what matters is the sort of norm of A minus A bar, right? So then I've just basically sort of shrunk or expanded my metric locally around the point A, right? So locally, it still really looks like the topology on the space I started with, but globally, I changed it quite a lot, right? So globally now it looks like this kind of teardrop, which gets sort of very narrow as you go out. Yeah. And you see, so why is that useful? Well, because now in this topology, if I look at 2 gauge orbits, right? So I have an A here and an A bar. Well, you know, they are going to sort of look like that. And I know from the thing that was written here and I've just erased that, you know, they will look like that in the sense that if G gets big, I know that I'm going to end up there, so far in the teardrop, right? Because I know that AG is bigger than G, basically, okay, if A is of order 1. So I know that I go out up in the neck. And then they are out in the neck, well, the difference between any 2 orbits is going to be very small. And so it's just going to not, at some point out there, it just doesn't contribute to this Hausdorff distance anymore, right? And so it means that this Hausdorff distance between any 2 guys, first, it's automatically going to be finite now, right? Because it's really just some sort of stuff that happens in some kind of ball of order 1 that really matters. And yeah, and it's really, I mean, it's not very difficult to see that now this does actually, the Hausdorff distance with respect to that metric does really metrize the quotient topology. Okay, so it's sort of, it's finite and it metrizes the quotient topology. And you can check that it's complete. It's sort of a bit more painful, but you know, it's not too difficult to check that this metric actually ends up being complete. Okay, one has to be a bit careful because the gauge orbits are not compact. Right? So it's always, it's a Hausdorff distance, but it's between non-compact sets. Okay, so so that was about the state space in 2 dimensions. And then, okay, so it's sort of the end of my time for today. So I just wanted to make a couple of, so maybe I'm going to spend sort of maybe 10 minutes or so explain what we do in 3 dimensions. So in 3 dimensions, basically nothing of what I said today works, right? Because, I mean, for starters, even if you could lift the 3D Gaussian free field to lines, which you cannot, here you are at best in C minus a half minus delta. So the best alpha you could hope for is a half minus delta. But then we've seen already that alpha needs to be bigger than 2/3 in order to actually restrict yourself to smooth curves. So there's basically no chance of having anything like that construction work. But it turns out that we can still, I mean, we can do less in 3 dimensions. So the picture is not as clean and complete somehow as we have it here in 2 dimensions. What we can do is we can at least have a reasonable notion of gauge orbit. Okay, so we can have a notion of equivalence. We can have a natural notion. We can, okay, so let's see. So we can define a natural state space on which, even though Wilson loop observables don't make sense, but we still have some kind of smoothened Wilson loop observables. And even though we don't have a nice gauge group so that the action of it has closed orbits, but we do have a notion of gauge equivalence, which is closed in the sense that, right, like the equivalence classes are closed sets. And that at least then tells you that the quotient space is sort of not too badly behaved. So it's not too pathological somehow from a topological point of view, okay? So we have some kind of partial results like that in 3 dimensions, but it's nowhere near as complete and clean as what we have in 2 dimensions. And so what I mostly want to do tomorrow is then discuss this whole question of gauge invariance, right? So we've seen yesterday, well, Tuesday, that in order to give a meaning to that equation, you really have to mollify that guy, but remove a sort of C epsilon A. And then in principle, the C epsilon A here breaks gauge invariance, but actually mollifying breaks gauge invariance as well. And so then the hope is that you're breaking it in 2 different ways that cancel out somehow. And of course, at fixed epsilon, they don't cancel out at all. But you can actually prove that if you choose the C epsilon in the right way, that they do actually end up canceling out in the limit as epsilon goes to 0. Okay, and so that's why I want to argue a bit. I want to show you tomorrow somehow a little bit how the argument works. And that's the argument which is really based on the sort of symmetry argument that Harpreet was showing in the exercises. Right? So remember yesterday Harpreet was showing that for rough differential equations, somehow the reason why you don't hardly ever have renormalization constants showing up was because if the driving path is symmetric on the time reversal, then renormalization constants have to be finite, and therefore you can choose them 0 in a natural way. And here, there's somehow, for a similar reason, the C epsilon does not have to be finite. In 2 dimension, actually, it so happens that it will be finite. But that's some kind of 2-dimensional magic. In 3 dimension, it's not. But still, we exploit somehow the gauge symmetry. We're able to exploit the gauge symmetry. I mean, it's sort of a funny argument because in some sense you exploit gauge symmetry in order to show that you have gauge symmetry in the limits. But you'll see that, I mean, the argument still, closes up without biting its tail. So, okay. So that's it for today, I think. Thanks.
Thank you, Martin. So are there questions or comments? Any question, comment? Can I ask you about, so this theory about the generalized one forms, this works in every dimension, right? Or at least two and more, or not?
Sorry, in any dimension?
Yeah, yeah.
Well, I think some bits work in any dimensions. Of course, the definition works in any dimension. One has to be a little bit okay. So I think most of what I talked about sort of works in any dimension. I thought there was some bit in the paper that sort of that didn't work in dimension, because there was at some point we were actually writing the whole thing with an arbitrary D, the bit about the state space. And then as far as I remember, there was one point where somehow it was important that dimension was 2, but I don't quite remember which point it was. I think what I told today, I think pretty much all of that works in arbitrary dimension, but I couldn't completely swear it.
So this quotient space, it doesn't look the same for different alphas, right?
This space?
Yeah. So in a sense, does the equation, the solutions, the theory that you're building up depends on the alpha in some way?
No. So we need, I mean, alpha needs to be, well, okay, so of course it needs to be bigger than 2/3 in order to be able to do this whole restricting thing. And of course it needs to be strictly less than 1 if you want the solutions to belong to it. But then, so in terms of like the initial data here, you can take it, so what's the worst? You can, yeah, so actually up 2/3 is good enough, I think. Yes, I think 2/3 is good enough. So I think you can take, for alpha, you can probably take anything between 2/3 and 1, and I don't think that that makes any sort of substantial difference to the solution theory. Right? I mean, like the solution itself belongs to all of them, and then it's just about whether you can start the solution with initial data in that space. Right, so if you somehow make your state space bigger and you want it to be a proper sort of Markov process with transition probabilities on that space, you want to be able to actually start with initial data, arbitrary initial data in that space. And then if alpha gets smaller, that may a priori be slightly harder. But in 2 dimensions, I think down to 2/3, I think it's, okay. I don't think there's a problem.
Okay, thank you.
For questions?
In 3 dimensions, this is more delicate.
Any other question? So if not, let's thank Martin again, please. So now we have a coffee break and the poster session, okay?
I think I'm probably going to stay around here.
So, welcome back. I'd like to introduce Ajay Chandra from Imperial College London. Please, let's start our talk.
All right. So thanks again to the organizers for putting on this great conference and for giving me the opportunity to speak. So I'll be talking about some joint work with Hendrik Weber, who is now at Münster, and Trish Ganaratnam, who was at the time our PhD student, but is now doing a postdoc at Geneva. So this is going to be about looking at large-scale properties of the 543 quantum field theory. And to begin with, oops, that slide's not supposed to be there. So to begin with, I wanted to say a bit about what the 5,4D Euclidean quantum field theory is. So just like the Yang-Mills measure, you can imagine writing down a formal expression for this measure as some sort of Gibbs factor against some infinite dimensional Lebesgue measure. And so in this case, the objects are going to be a little bit less exotic. So the fundamental object is going to formally be a real scalar field. So that's just some function from RD to R. And the action, let's see how this, oops. Oh, I shouldn't have done that, I guess. Good. How do I, oh, this. Good, okay. So the action is given by a gradient squared term, which we think of as a kinetic part, along with this local term here. And so the 5,4 is why this is called the 5,4 model. And so this model has a pretty rich history at this point. So it was one of the primary models that was studied in constructive field theory in the 60s and 70s and later. So I want to talk a little bit about how we make this. So everything on this slide is completely formal, right? Because again, as you saw in the lectures on Yang-Mills, you don't really have a notion of Lebesgue measure in an infinite dimensional setting. Now, our situation is a little bit easier because what we can do is we can take this quadratic part or the kinetic part and look at that as the action of a Gaussian measure. So instead of writing the measure as a perturbation of Lebesgue measure, what we'll do is we'll use that action to define a background Gaussian measure, which is just going to be the Gaussian free field. And then we treat the rest of the action as a local perturbation of the background Gaussian measure. So this is a little bit less formal, but still completely, still not something that's completely rigorous because in principle, so in the situations that we're interested in, which are going to be 2 and 3 space-time dimensions, or D equals 2 or 3, this Gaussian measure is not going to be supported on a space of functions, but will be supported on a space of distributions. So so here, these nonlinear expressions in the underlying field don't make sense on the support of this measure. Another issue which that appears in this problem is that you're also dealing with a Gibbs factor in infinite volume. So even if these were functions, even if the small scale regularity was dealt with formally, this isn't a rigorous expression because of this integral here. Okay, so this is, and you already see in some sense that life is a little bit easier than the Yang-Mills model, because here there's a nice splitting into a non-degenerate Gaussian with a kind of interaction perturbation. So phi4 is quite a bit friendlier than the Yang-Mills model. Okay. So how you actually make sense of this is you introduce cutoffs, and so we'll introduce both cutoffs to deal with the ultraviolet singularities or the small scale irregularity and the issue of infinite volume. So to do that, we'll start looking, so we'll localize the model and work on a torus, a d-dimensional torus of side length n, and then replace the Gaussian measure you saw before with a Gaussian measure on fields on the torus, where I'm going to put in a Fourier multiplier to suppress Fourier modes that are too large. So here, n and k, you can think about them as natural numbers. And so what I'm going to do is I'm going to basically suppress large Fourier modes so that now this is a Gaussian measure that actually is supported on bona fide functions from the torus into the real numbers. Okay. And so I need to tell you, so I've told you what this guy is. This is just a normalization factor, which will turn out to be important later. Any questions so far? Mm-hmm. That's right. Yeah. So in principle here, the lattice, going to the lattice is another perfectly good way to deal with the small scale irregularity. That's right. Yeah. Yeah. Any other questions? Okay. Great. So what about the potential here? So the idea is, in this expression, the meaningful object, the kind of formal object that I wrote down on the previous slide, we want to think about that as an n goes to infinity, k goes to infinity limit of these measures. And so, especially for the k going to infinity limit to actually make sense, the interaction is going to have to be modified. So we're going to have to introduce counter terms. So this is renormalization. And so what you'll have to do is you'll have to introduce a term that's proportional to phi squared. So there are two renormalization counter terms, one at order g squared and one at order g. And one of them blows up logarithmically in the cutoff, and the other one blows up linearly in the cutoff. And I've also put down, if you look at the literature, you'll also sometimes see a constant renormalization that might look a little bit silly, because if we're looking at a probability measure, this will be annihilated by the normalization factor. But it turns out to be beneficial when you're stating statements about estimates on things like the partition function. And so I want to just point out that these things, if you're, the kind of big picture is that we're trying to do statistical mechanics for these this Euclidean quantum field theory. So I should have said earlier, but I changed the D to a 3 here. This structure here is specific to 3 dimensions. So the idea is if you're doing statistical mechanics here, you can't ignore the small scale behavior because it's actually dramatically changing the structure of your model. So if you had a kind of convex potential, or maybe a critical potential, or maybe a double well potential, it somehow doesn't matter if you're looking at the bare potential. So what's up here, because the sign of these guys, so I didn't tell you this, the precise sign of these constants, is going to mean that you're going to basically go into a situation where you have a really deep double well that's becoming infinitely deep as you remove the ultraviolet cutoff. Okay, so that will be a little bit important later. But the idea is that, again, the limiting object, the thing that everyone hopes to construct, or I mean has been constructed in some landmark papers, are the k goes to infinity, n goes to infinity limit of these measures, which k going to infinity is sometimes called the ultraviolet limit, n going to infinity I'll call the infinite volume limit. And I'm not going to state all of them here, but the original motivation for constructing these probability measures was to basically use them to actually build physical quantum field theories. So quantum field theories living in Minkowski space. That is to say that, the people who, we shouldn't just go back to sleep after constructing these limits. There are lots of important things to do afterwards. Okay, so I wanted to talk a little bit about what happens in various dimensions with the 5,4D model, and I'm not giving a full list of literature here, and I'm not even kind of naming the very first people who dealt with various parts, but basically I'm listing the people who verified the axioms in the dimensions 3 and lower, well, dimensions 2 and 3. So in dimension 1, the Gaussian that you're perturbing against is actually fairly irregular. So it's supported on function. So no renormalization is needed. In dimension 2, that's the first place where you see the need for renormalization, and an infinite volume measure with the ultraviolet limit taken as well was constructed in a paper by Glim, Jaffe, and Spencer in 1974. And while 2 dimensions is an interesting kind of first taste of renormalization, it has a feature that simplifies its analysis quite a bit, which is that the measure is absolutely continuous with respect to the Gaussian before you take the infinite volume limit. So in dimension 3, the renormalization is more complicated. So you see what are called non-local divergences, and the measure is the measure is singular with respect to the Gaussian, even when you're in finite volume. And so those are sort of positive stories. So we also have no-go statements. So in dimensions greater than 4, Eisenman and Froelich proved that if you try to construct these measures, then any kind of renormalization method that you use is going to mostly kill the nonlinearity, so that you're going to be left with a Gaussian. And that's uninteresting for us, or well, for the physicists, it's not so interesting in this case, because the idea is that we want to use these measures along with the Osterwalder-Schroeder axioms to build interacting quantum field theories. And intuitively, you can think about interacting as meaning non-Gaussian. And then the dimension 4 case was technically quite challenging, and has only recently been settled by Eisenman and Duminel-Copan in 2019, which is again a triviality statement, which is saying that you know, how if under a kind of wide scheme of renormalization methods, any limit that you get is going to be a Gaussian limit. Well, I mean, honestly, I think you can find people in both camps on that story. I mean, there are people who, I think the traditional view is that that it's impossible to build the 5,4D model in non-trivial 5,4D limit in dimensions 4 and higher. That doesn't mean that there's no hope of building quantum field theories in 4 dimensions, because 5,4D is not the standard model. It's a kind of very simple quantum field theory. So, so in the non-abelian case, there could be a different story, a non-abelian gauge theory. But there are people who, you know, think maybe a different point of, I mean, you could say that, you know, I can build a 4-dimensional classical field theory. Why can't I quantize it? So there, I mean, there are people who are still thinking about it, but I would say that the vast majority think that such a construction isn't possible. Okay. Any other questions? All right. Yeah, so this talk is going to be on the large-scale properties of 543. And so by large scale, we mean infinite volume or macroscopic. And so we're interested in the large N behavior of this observable, which is, I've called M because you should think of it as the average magnetization. So, so now what we're going to be doing is making an analogy between the 5,4 model and Ising, and we're going to be thinking about this field as a spin field. Again, in the limiting measure, you expect this field to actually be a distribution. So, but as I'm going to explain, there's a relationship between this model and the Ising model as a model of ferromagnetism. And so the punchline of the talk, or what we further develop, is that in certain parameter regimes, the 543 model should be described by an effective theory which resembles the Ising model in the phase coexistence regime. So, so the rest of the talk is going to be about making this precise. So let me talk about the Ising model. So the Ising model is a model of statistical mechanics. And so what I'm going to do is I'm going to look at a finite box on the integer lattice with periodic boundary conditions. And so here we'll start by defining a measure on finite volume configurations. So a configuration is just a map from the box into -1, 1, and then given a lattice site, sigma I is the spin's value at that lattice site. And the idea is that we're going to weight these configurations by first starting with a product Bernoulli measure. So that means we take value -1 and 1, each with probability 1/2. And then we weight it with this Gibbs factor. So here, I'm summing over nearest neighbor pairs in my box, and I'm multiplying by a coupling constant, which we call the inverse temperature, beta. And so what you should imagine is that this Gibbs factor is rewarding configurations when spins at nearest neighbor sites are taking the same value and penalizing configurations when that doesn't happen. Okay. If you take the infinite volume limit, there are a variety of methods you can use to argue that, that such a limit exists. But what's important, the main story here is that the Ising model has a phase transition when the dimension of the underlying lattice is 2 or higher. And there are lots of different ways to describe what we mean by phase transition here. But I'm going to try to describe things just, in this case, using the 2-point function. So if I look at the correlation between 2 spins under this infinite volume measure, then I see 2 different regimes as I send these 2 lattice locations infinitely far apart. So there's one regime when beta is small, and so since beta is the inverse temperature, we call this oftentimes the high temperature regime. This is going to exponentially decay in the distance I minus j. There's another regime where there's a phenomenon called long-range order, where this quantity is uniformly bounded below by a positive constant, irrespective of how far how far away I and j are from each other. And then there's a critical point that that splits these 2 regimes. So there's a sharp transition here for the nearest neighbor Ising model. Okay. Good. So, I mean, I'm sure many people here have seen this before, but just some background. And so what you should imagine is there's a battle here between the kind of, the spins wanting to be completely independent and this kind of interaction making them feel each other. And so what's happening here is the cooperative effect takes over once this factor is strong enough. Okay. You can also talk about this at the level of dynamics. So if you looked at the spectral gap of this measure, then what you expect is that in the high temperature regime, the spectral gap, so what's important here is the behavior in n, the system size. And so what you expect is that the spectral, it's also been proven that the spectral gap is bounded below by a positive constant in the high temperature phase. And then the spectral gap is decaying at least this fast in the low temperature phase. And so here, so what's happening is somehow what we see here is a surface order cost here that's kind of driving down the spectral gap. And so part of the talk will be kind of talking about how this happens. Good, okay. Any questions so far? Okay. Intuition. So what do configurations look like? Well, in the high temperature phase, so beta smaller than the critical value, then spins are mostly free to do what they want. And then in the low temperature regime, when beta is larger than beta c, then what you expect is the bimodal well, the magnetization would have a bimodal distribution, which tells you that basically you expect to see mostly pluses or mostly minuses. And in particular, you also expect to see this, even if you have, mostly pluses and a few minuses, you expect more. You expect the minuses to want to stick together, for instance, here, or the pluses to stick together here. So you expect configurations that minimize the total amount of interface that exists between pluses and minuses, because that's what's energetically expensive. And then if you looked at the low temperature regime, but you said that I want to actually condition on the magnetization being small, then what you can prove is that you expect to see macroscopic contours. So beyond just looking at phase transitions in 543, what we're actually going to be talking about is this phenomenon of phase segregation in 543. What's important here is that this allows you to identify the surface order energy cost. So this is telling me how costly it is for the magnetization to be near zero. So essentially the rest of the talk is going to be explaining, how we can talk about this sort of story for the 543 Euclidean quantum field theory. Okay, good. Okay, so we're going to look at 5.4 in the low temperature regime. And here, what I've done is I'm still working on a finite torus, but I'm pretending that I'm not worried about the ultraviolet limit, just to write down the interaction. And so what I'm going to do is I'm going to, I have the same kinetic part here, but now I have a particular form for the quartic polynomial, the local polynomial that's giving me the interaction, the word interaction here is maybe not the best word to use. But here, if you think about things this way, it's a little bit clearer how we can think about a 5.4 model as corresponding to a low temperature Ising model. So you should think about the gradient squared term as encoding a spin-spin interaction, a local spin-spin interaction. And then this thing for beta large enough, well, actually you can just think about beta positive for now. This thing corresponds to the Bernoulli measure to some degree. So this is, you can think about this as your single spin distribution. Okay. So what we're going to do is we're going to think about the lattice for the Ising model as actually corresponding to a tiling of the n-dimensional torus by unit blocks. So you can think about these unit blocks sitting at, with integer vertices. And so the principle is that if you take so here this is just a formal expression, but if you renormalize this and then take the limit, and then you smear the field with indicator functions for these unit blocks, then you have a system that is living on a discrete lattice but takes continuous values. So this is sort of like a continuous spin Ising model living on the discrete lattice. And what I'm going to be describing is how you can actually show that this behaves like low temperature Ising. All right. And so this is, there are lots of different relationships between the 5.4 model and the Ising model. So most of the time people are interested in going from Ising to 5.4. So here we're going from 5.4 to Ising. But yeah, you should think about this as trying to describe an effective theory. You know, it's to some degree, it may seem like something that makes sense intuitively, but technically it's actually pretty demanding in order to show that this actually works. Okay. So here's the proof with Trish and Hendrik. So for any delta between 0 and 1, there exists some beta naught, some positive constant C, and some n naught, such that if you look at any beta greater than beta naught, and you look at n greater than n naught dyadic, then the probability of the average magnetization being this close to 0 decays with this rate. So this probability decays like e to the minus this times n squared. Okay. So that's the main result. And so I want to say that, okay, the corresponding results for Ising have been proved. Schonman proved it in 87 for the 2-dimensional Ising model, and Pistora proved it in 96 for the 3-dimensional Ising model. I also want to say that this also gives you decay of the spectral gap, which was also our first motivation for looking at this problem, trying to see the signs of the phase transition dynamically. And then I want to say that I want to just point out that the kind of the high temperature regime has actually fairly recently been done for 543. So a lower bound, well, log Sobolev inequalities were proved for 543 in the high temperature regime. Okay, any questions? Okay. Great. So I want to talk about, so this problem was, trying to think about the 5-4 model as an Ising model was done before, fairly early in this game. In 1975, for low temperature 542, Glim, Jaffe, and Spencer proved this long range order bound. So basically looking at the covariance that the spin at one site is positive and that the spin at another site is negative, and showing that in absolute value, this is bounded below uniform in the lattice distance. There's also past work on 543. Part of what was interesting about this problem is that, if you kind of think in terms of statistical mechanics, the argument that's used for 2 dimensions here is not so different than the argument for 3 dimensions. So once you understand the 3-dimensional argument, it kind of implies the 2-dimensional argument, the 2-dimensional result, just with some minor modifications. But the issue is that, we're talking about long-range behavior, but what we really have to fight with throughout the whole problem is the fact that we also have to renormalize small-scale divergences. And so, in the heyday of constructive field theory, and also I think up until recently, the technology to kind of both deal with the ultraviolet renormalization and also kind of show that it effectively acts like an Ising model, I would say didn't quite exist until fairly recently. And so the previous work on 543 uses reflection positivity. So it uses a softer argument called so it obtains an infrared bound to prove the phase transition. It's a kind of, it's a very important method in mathematical physics, but it's totally unclear how to make this method quantitative. So this result here is used by establishing, well, it's proven by establishing contour bounds for the 542 Euclidean field theory. from which you can begin to kind of actually detect, what is the energy cost of the magnetization being 0. But reflection positivity by itself, if there is a way to do it, that would be super interesting, but it's unclear how to extract a quantitative result from this proof. Okay. And so I'll just kind of briefly talk about the steps of the argument. And so what we do is we look at first look at the system as an ensemble of defects. Okay, so what is a defect? Well, it's easier for me to tell you what isn't a defect. So here, these are the unit blocks, and I've put blue dots and red dots here. And if you have a square with a blue dot in it, that means that it means two things are true. If I take the integral of the field on that block, it's localized in this regime, this kind of region on the non-renormalized potential, and you can control the average of the pointwise square on that block with the square of the average. Okay, so here you have to use the Wick square, but I don't want to get into that. Okay, and so we say that, so here, these guys aren't defects because they're localized like this, and this is controlled, and they're surrounded by sites, so they have a star neighborhood of blocks that also satisfy the same property. And so what you should imagine, I can just say it here. If you have, the key idea is that we want to get an estimate that's robust in the ultraviolet limit that says that that extracts this cost for defects. Okay, so if you have a collection of unit blocks A that are defects, and you're saying all of them are defects, then we should get this exponentially small factor to penalize this happening. And here, so the square root of beta is kind of optimal, but this is also a sign that we're really working in low temperature. So the principle is that, we have this kind of gas of defects, and we're going to look at what can happen with configurations here of these unit blocks. And there are going to be good energy factors and bad entropy factors. And this sort of bound allows us to beat entropy factors by going sufficiently low temperature. So it's the same thing that you see in the classical Peierls argument. Except you have a different, instead of just contours, we're working with these things called defects. So a defect is when neither of these things are true. And so, why do you extract this factor when neither of these things are true? Well, if one of these guys is not localized, then there's a good factor, right? Because then you're not on the lowest point on this potential. And if you had something like a red dot next to a blue dot, then then you're going to actually have a good factor from the Gaussian part. Okay. So the second step of the argument is that you don't see in the Ising story is you also need to control very large fields, because you can control, so a very large field is a defect, and maybe you can control how many defects there are, but the field could potentially be arbitrarily large on few defects and then totally mess up your whole geometric picture. So the other thing that you can do is you can kind of show volume order bounds to control these very large fields. And then the last part is to step that is sometimes called controlling the gas of small contours. So the idea is that if you just think naively, having all the minuses on one side and all the pluses on one side is a kind of organized way to do things that minimizes the energy. But the issue is that having lots of islands of pluses and minuses all around each other is energy expensive, but is entropically favored. So what you have to do is you have to kind of identify a certain length scale that allows you to show that the real leading contribution does come from large contours. Okay, and so we can mostly follow the Ising literature for this. So there's lots of work on using these contours. There's also like the really nice work on the Wolf construction and so on. But our kind of method on this is we follow work by Bodno, Joffe, and Velenik. So we kind of adapt their analysis to our sort of effective Ising model. And so the defect bounds, okay, so I mean, I think there's sort of a whole school of mathematical physics where basically, whatever you're trying to prove, at the end of the day, you're trying to estimate a partition function. And so the key input here are those defect bounds come from sort of exponential Chebyshev bounds that use exponential moments of these observables. So so what we do is we introduce these functionals that are indexed by blocks or pairs of blocks. And so what you should imagine is that these functionals are small when there isn't a defect present, but they're either really positive or really negative when there is a defect present. And so here, this is the kind of localization in the well. This is the average of the square being close to the square of the average. And then this is the interaction. And so the spin-spin interaction. So these two things are mostly controlled using the potential. And then you should think about this as being controlled by the Gaussian. And so the bound that we prove is if you have collections B1 of blocks, connect a collection B2 of other blocks, and then collection B3 of pairs of nearest neighbor blocks, then you get this sort of extensive, I'm missing a parentheses here, but you get this sort of extensive bound on this sort of observable under the measure with the ultraviolet limit removed. And in particular, you want this bound to be uniform for beta large. Okay. And so then if you have this estimate, it's a kind of fairly straightforward thing to get those defect bounds I was talking about. Okay, good. And so how we get those bounds are by estimating a partition function and then using chessboard estimates. So so what we do is we obtain those bounds by proving an ultraviolet stability estimate. So we prove that some object, well, the partition function is bounded, and I should say, it's also uniform in N here. That's important. So you need to estimate this quantity uniformly in K, N, and beta. So this Z tilde Kn is like the partition function or the normalizing factor I wrote down before. It would be the exact same thing if I erase this, except I also introduce a new functional, which you should think of as basically the Q's made isotropic. So essentially what this means is I take the Q's and I put them on every block. or every pair of nearest neighbor blocks. And then this V beta Kn, this is the renormalized low temperature potential. So it looks like the kind of the well with minima at plus or minus square root beta, but then it's renormalized, which makes it look quite different. And the idea here, so I won't explain chessboard estimates, but the story is that you know, if I wanted to just get the bounds that I had on the last page, the defect bound, then what I would want is I'd want to be able to see that if I looked at a ratio of partition functions and I put this in one region, maybe on half the volume, then I would get that the ratio of partition functions, if I take the log, behaves like, you know, half and 2. So what chessboard estimates allow you to do is they basically allow you to get estimates that are extensive in kind of smaller volumes by getting an estimate that is extensive in the entire whole. It's not for free, so again, this requires reflection positivity, which is a thing that disappointed us. But while our proof also uses reflection positivity that's involved in these chessboard estimates, it gives you more information than reflection positivity by itself would give you. Good. And so then the key tool for proving this, and this, I mean, when I was saying before that, I think the previous methods for studying 543 would make understanding this very difficult. The key new ingredient that allowed us to do this was an approach developed by Barashkov and Gubinelli, which is a variational formula for Euclidean quantum field theories. I won't be able to describe it in full detail, but I just wanted to give a little bit of an idea. And so to get an intuitive feeling for what this variational approach is, I'm going to talk about an earlier result that kind of, contains a lot of the key ideas. So this is a theorem by Brouet and Dupuy. And in this setting, you have an n-dimensional Brownian motion, and then you have some bounded measurable function of your Brownian motion, of the entire trajectory. And so here, the Brouet-Dupuy formula gives you a formula. Oh, okay, this is bad. So there should be an E here. It's exponential of this. So minus log of exponential e to the minus h of b is given by this variational formula, where you take an infimum over adapted bounded processes, and you take the expectation. So here there should be an exponential, and part of the magic is on the right-hand side, there is no exponential. So you evaluate the functional on the Brownian motion, plus the kind of integrated adapted bounded process, and then you also have this L2 norm here. And so this is, you should think about this as a sort of beefed up version of the Gibbs variational principle, where I don't know why I forgot these E's. Okay, there's an E here too, but the log of the expectation of e to the minus h is equal to the infimum over a class of probability measures of the expectation of h plus a relative entropy term. And so why you can beef this up using stochastic analysis is that we understand very well. So when we're working with the measure for Brownian motion, we understand very well the measures that are absolutely continuous with respect to Brownian motion because of the Pearson Good. And so if you want to understand, okay, what's the idea behind the Gubinelli method in a kind of very summarized way, well, that's going to be for working with this infinite dimensional Brownian motion, where the Brownian motion at a given time is actually a regularized Gaussian free field. And so here, the time parameter will actually correspond to an ultraviolet cutoff on the Gaussian free field. So as you send t to infinity, you recover the unregularized Gaussian free field. And so, so what's nice about this, and this is sort of where singular SPD enters the picture, is, so first thing is, you know, one of the key successes of this method is proving ultraviolet stability for 543. And what you see for 543 is that you actually need to work to actually find this, to find a pretty good drift. And that pretty good drift is actually given by a power-controlled ansatz, which is, you know, essentially, I mean, it's sort of the elliptic setting, but it's what you see in the power-controlled ansatz for solving 543. So, okay, you can't just take what they prove and apply it to our method, and so there's quite a bit of extra work to do, because that that method, if you just applied it to our model, would not give you bounds uniform in beta. And this is something that isn't so surprising if you looked at what happened in how people studied 542. And so what you need to do, and what I'm kind of really just summarizing here, is you need to perform a low temperature expansion. So what you need to do is you need to kind of you need to localize, you need to basically localize to spin configurations. I mean, you basically look at spins that are all localized in one well or the other, and then you expand about them. So you're basically summing over a whole bunch of mean fields, which are all kind of localized in different ways. And then you look at the difference between the real field and these mean fields. And in principle, you know, what you see there is you see something that depends on basically fluctuations of the field. And so what you can do is you can basically decompose this problem into kind of an effective Hamiltonian, which, you know, involves basically the things that are localized, and then a whole bunch of mess which involves small scale degrees of freedom. And then you can use Barashkov-Gubinelli to control the small scales. Okay, so that's and I think that's, I mean, that's basically where most of the kind of new work is in kind of carrying out this program. So possible future directions are that it would be nice to strengthen this Barashkov-Gubinelli method so that we didn't need to use chessboard estimates. So, I mean, there are, you know, if it's easy to come up with models for which chessboard estimates don't hold, or you don't have reflection positivity. That's more accurate for me to say. And the kind of real technical heart of our method doesn't really use chessboard estimates. The other thing that would be nice to do is to push the analysis to cover the full low temperature regime. So we need to take beta sufficiently large. It would be, you know, it would be interesting to see if, I mean, how you could argue, and this has been done in the Ising case, to try to go all the way to the critical point. And then another interesting direction, and you have to, I mean, how this would be defined, you'd need to kind of give some thought to, is to develop a theory of phase interfaces for low temperature 542 and 543. So for the two-dimensional Ising model, if you look at the model of the box and you put pluses on one side and you put minuses on the other, and then you perform a sort of scaling limit, then you'll see that there'll be a kind of macroscopic interface that actually converges to a Brownian bridge. While in the three-dimensional Ising model, you will have, so a Brownian bridge actually, a Brownian bridge delocalizes, right? So then what happens, what that means is, in the end, either the pluses win or the minuses win. In 543, you actually can see a stable interface. Well, for the three-dimensional Ising model, you can see a stable interface under the analogous boundary condition. The fluctuations around this interface are still not, they're an active area of research. So we know that that the interface is stable, but people don't really understand this interface as a random field. So I think the natural thing to do is to try to understand or come up with some sort of theory of interfaces, maybe for low temperature 542. Okay, all right, and so thanks for listening.
So questions, comments?
Hey AJ, so about this infinite dimensional Brownian motion variational representation, I'm aware that Paul Dupuy also has developed, there is the finite dimensional one, and he also has a paper for the infinite dimensional one. I was wondering what's the difference between the one that you mentioned and the one that already existed. If you've seen something like that.
Yeah, I think the let's see. Yeah, I think I'm not familiar with the kind of other infinite dimensional analog. I do know that, for one thing, in this setting, our H is not bounded measurable. So that introduces...
Okay, yeah, that makes sense. Yeah. Because the one that already existed was for bounded functionals. Right. Yeah, thank you.
And then you also, and then when you do that, basically the space of drifts, when you kind of relax that assumption, the space of drifts becomes replaced with a kind of slightly more complicated construction. Yeah.
Thank you.
Further questions?
Could you say what you mean by a Brownian bridge delocalized? At the end, you were kind of...
Well, okay, so if you look at a square box on the two-dimensional lattice, and you put pluses on one half of the perimeter and minuses on the other, then you'll see a kind of random curve that goes from one side to the other. And then you can kind of take an infinite volume limit along with a corresponding scaling to get basically a Brownian bridge. So this has been proven. This also kind of tells you, this is also a sign that, that's one of the ways that I think about the fact that there's this thing called the Eisenman-Higuchi theorem, which basically says that all Gibbsian measures for the two-dimensional Ising model are translation invariant. So naively, you could think that in the two-dimensional Ising model, you could put pluses on one side and minuses on the other, and you could have some happy infinite volume measure where the pluses live on their side of the fence and the minuses live on the other. But the fact that you get this Brownian bridge, I think, indicates that that doesn't really happen. Just because, yeah, a really long Brownian bridge is going to kind of delocalize.
Thank you.
And in 3 dimensions, that is possible. In 3 dimensions, there is a non-translation invariant Gibbs state.
Thank you.
Any more questions? So, if not, let's thank Ajay Chandra.